Vacuum energy is a perplexing concept that challenges our understanding of what empty space actually means. At first glance, the vacuum, or the seemingly empty space between celestial bodies, seems like a complete void, nothing but emptiness. But quantum physics paints a different picture. It reveals that even in the absence of visible matter or radiation, space is far from empty. In fact, it's teeming with energetic fluctuations, where particles and antiparticles appear and vanish in an ongoing cycle. This unseen energy is called vacuum energy, and it exists throughout the entire universe in every corner of space. This idea challenges our classical understanding of a vacuum, which we traditionally thought of as a complete lack of anything. Quantum physics, however, tells us that even without matter, there is still energy within the vacuum. This presents a major puzzle when we attempt to calculate the energy of this vacuum based on quantum physics principles. The calculations yield a value so large that it seems almost unbelievable, up to 10 circumflex 120 times greater than the energy observed in the universe today. This staggering discrepancy is considered one of the biggest errors in the history of science. If such enormous energy existed, it would have caused the universe to collapse shortly after the Big Bang. Yet, the universe we observe is stable, with no such collapse. This paradox raises a crucial question. Why does the vacuum energy seem so low? To explain this, scientists often refer to the cosmological constant, a concept introduced by Einstein. The cosmological constant represents a repulsive force within the fabric of space-time, counteracting gravity's pull. Instead of causing the universe to collapse, this force makes the universe slowly expand, as though a subtle force is gently pushing everything apart. However, the cosmological constant raises another mystery. Why is it so small, and why does it exist in its current form? Despite several theories, no one truly knows why the constant has the value it does, or why such a tiny amount of vacuum energy remains. Some theories suggest an extreme fine-tuning, questioning the delicate balance between the laws of nature. Other ideas propose dynamic mechanisms where fields adjust themselves over time. However, no one theory has gained universal acceptance. Vacuum energy is not just a theoretical concept. It has tangible effects on the universe's expansion and structure. It is linked to what we call dark energy, a mysterious force accelerating the expansion of the cosmos. In fact, the observed dark energy could be a large-scale manifestation of vacuum energy, implying that understanding vacuum energy is crucial to understanding the universe's future. But as of now, the evidence remains incomplete. Experiments from the Planck satellite, the Hubble telescope, and the Uccle Observatory are all aimed at refining our measurements of cosmological parameters. By examining the rate of expansion and the distribution of galaxies, scientists hope to uncover more clues about dark energy. So far, the observed value of vacuum energy is incredibly small, while theoretical predictions suggest an almost infinite amount. This contradiction continues to baffle scientists and remains one of the biggest unsolved problems in modern physics. Some physicists look to string theory for answers. In string theory, particles are seen as tiny vibrating strings that exist across multiple dimensions. This theory suggests that there may be a vast landscape of potential universes, each with different values for fundamental constants. Perhaps we were just fortunate to live in a universe where vacuum energy is low enough to allow atoms, stars, and galaxies to form. But this idea opens up a new question. How can we test the theory of a multiverse, or the fine-tuning of the cosmological constant? At present, no practical experiments can directly verify these ideas. As a result, the problem of vacuum energy remains a grey area, straddling the line between established physics and speculative thought. The influence of vacuum energy on the cosmos, however, is undeniable. It lies at the intersection of two of the most fundamental pillars of modern physics, general relativity and quantum mechanics. General relativity describes gravity as the curvature of space-time, while quantum mechanics focuses on particles and forces at the subatomic level. The mystery of vacuum energy sits exactly between these two worlds, and finding a unified theory that incorporates both may be the key to solving this riddle. Meanwhile, observations show that the universe's expansion is accelerating at an ever-increasing rate, consistent with the presence of a small constant energy filling all of space. In simpler terms, the vacuum is not neutral. It exerts a gentle push on the universe. But why this push is so weak and not a force strong enough to tear everything apart is still a question without a clear answer. We are left observing the phenomenon, but the origins remain elusive. As researchers continue to investigate theoretical and observational models, we may eventually find a way to reconcile the predictions with what we actually observe. Future breakthroughs, such as more accurate measurements of gravitational lensing, galaxy spectra, and variations in the Hubble constant, may provide more precise data. Meanwhile, concepts like supersymmetry or fluctuations in scalar fields are being explored for potential answers. But for now, the problem remains open, one of the great unresolved questions at the crossroads of quantum physics and cosmology. Particle physics experiments, such as those at the Large Hadron Collider (LHC), are exploring the potential existence of more intense asymmetric processes in the universe. At the same time, neutrino observatories like SuperComio and Dune are focused on investigating whether there are any violations in the symmetry of neutrino oscillations. These experiments hold the possibility of revealing a clue about what tipped the cosmic scale in favor of matter. The mere fact that we exist is a statistical anomaly, just a tiny detail in the immense scale of the primordial universe. But this small detail raises some profound questions. If the laws of physics are supposed to be symmetrical, why does reality appear so lopsided? Is there still something hidden in subatomic processes that could explain why matter took precedence over antimatter? Or do we simply live in one of the rare regions of the cosmos where this imbalance happened to occur? One hypothesis that arises in this context is the multiverse theory. While speculative, it suggests that within a universe that includes multiple inflationary regions, each could have had its own set of initial conditions. Some of these regions might have been dominated by antimatter, rendering them uninhabitable due to the inevitable annihilation between matter and antimatter. Perhaps we simply exist in the region where matter was the winner, and that's why we're able to ask these questions. However, this theory is not something we can directly test at the moment. Another theory proposes that antimatter could exist in large quantities in parts of the universe we haven't yet observed. This would require entire galaxies composed of antimatter, which doesn't match the gamma-ray emissions expected from the annihilation at the border between matter and antimatter. The lack of evidence for such emissions weakens this theory, but doesn't completely dismiss it. The mystery of baryonic asymmetry is not just a cosmological issue, but also an experimental one. We're dealing with an event that occurred in a fraction of a second after the Big Bang, a timescale so small that it's impossible to replicate the conditions in our labs. Yet, the universe has left behind faint traces, and physicists are constantly looking for any clues that might help solve this riddle. A small deviation in a particle's behavior could hold the key. This issue also touches upon the very nature of science itself. How much trust do we place in symmetries as fundamental principles, and how do we proceed when observable reality contradicts those symmetries? Should we revise the theoretical foundations, or do we need to discover a new particle altogether? Regardless of the direction, this investigation is tied to the very essence of our existence. Why is there something rather than nothing? Despite the advances in both experiments and theoretical models, the origin of this asymmetry remains unresolved. The universe, vast as it is, may still be offering us subtle clues through unstable particles or elusive neutrinos. Finding the answer will require a collaborative effort between theory, observation, and experimentation. Meanwhile, we can only marvel at the fact that every galaxy, star, and living being exists, because matter was ever so slightly favored over its opposite twin. Now let's dive into Olbers' paradox, the age-old question of why the night sky isn't fully illuminated. If the universe were infinite, static, and eternal, filled with stars in every direction, the night sky should be completely bright, not dark. This paradox, proposed in the 19th century, stems from a simple logic. If stars are scattered throughout space, their combined light should create a sky that glows in every direction. But that's not what we observe. The solution to this apparent contradiction lies in the nature of the universe itself. It's not eternal, and it's not static. It's expanding, and it had a beginning roughly 13.8 billion years ago. This means that the light from many distant stars hasn't had enough time to reach us. The farther a galaxy is, the more its light is stretched as the universe expands, causing the light to fade or become invisible. This stretching of light is known as redshift. Another factor that helps explain this paradox is the finite lifespan of stars. Stars don't shine forever. Even in regions full of galaxies, stars are born, burn through their fuel, and eventually stop emitting light. This further reduces the possibility of a constant uniform glow in the night sky. The finite lives of stars combined with the universe's expansion create a plausible explanation for why the sky doesn't shine with an unbroken glow. Additionally, interstellar dust absorbs and scatters some of the light from distant stars. While this doesn't fully account for the darkness we see, it does contribute to reducing the amount of light reaching us. When combined with the finite speed of light, this leads to an uneven distribution of brightness across the sky. Modern observations like deep field images of space support this understanding. Moreover, the cosmic microwave background radiation plays a role in explaining the paradox. This faint glow left over from the Big Bang fills the universe in the form of microwaves. Although we can't see it with the naked eye, it confirms that the universe had a hot and dense beginning. It's not visible light, but its presence reinforces the notion that the sky isn't empty. Instead, the limits of visible light's reach and origin are at play. As the universe continues to expand, the wavelengths of light stretch. Light from distant galaxies shifts from visible to infrared and even microwave wavelengths. So much of the light that would once have appeared in our visible sky is now shifted beyond our sight. What we perceive as darkness is partly a result of this transformation. Models that incorporate the accelerated expansion of the universe provide a comprehensive solution to Olbers' paradox. When we consider a universe with a finite beginning, the finite travel time of light, and the life cycles of stars, the paradox is resolved. Simulations that include these factors align perfectly with the sky we see today, full of discrete points of light, with vast dark expanses in between. This understanding supports the observational cosmology we rely on today. It's important to recognize that no single factor alone explains the darkness of the sky. Instead, it's a combination of expansion, stellar lifespans, light absorption, and redshift that together form a coherent explanation. The reasons behind the night sky's darkness can now be explained without relying on alternative hypotheses or forced theories. One key tool in this investigation is the observation of the universe's diffuse background across various wavelengths. Space telescopes like Hubble, Spitzer, and the James Webb Telescope detect light in parts of the spectrum our eyes can't perceive, revealing objects and emissions that contribute to the universe's total energy. However, a lot of this energy doesn't fall within the visible light spectrum, which only reinforces the dark appearance of the sky when observed with the naked eye. Olbers' paradox, which once seemed like an unsolvable mystery, has now been resolved within the framework of the standard cosmological model. It remains a fascinating topic for discussions about the limits of what we can observe, the nature of light, and the role of time in our understanding of the cosmos. Though it may seem like a simple question, solving it requires a comprehensive understanding of several interconnected physical principles. That's why this paradox is still widely discussed in introductory astronomy courses. As technology continues to improve, we will likely gain a deeper understanding of the universe's diffuse glow in all directions. Future, more precise measurements could reveal contributions from previously unidentified sources, such as ancient galaxies, active black holes, or transient events. While a complete overhaul of the paradox's explanation is unlikely, these new findings will enrich our knowledge of the cosmic background. Olbers' paradox has already been answered, but it remains a useful teaching tool. It connects logical reasoning, observational limits, and the fundamental properties of the universe. What began as an error in our model has now become an important stepping stone in our journey to understand the cosmos, coinciding with the rise of modern cosmology, which now accurately describes the universe's structure and evolution. Let's turn our attention to the cosmic microwave background, CMB, the oldest light we can detect in the universe. The CMB was emitted roughly 380,000 years after the Big Bang, at a time when the universe had cooled enough for protons and electrons to combine and form the first hydrogen atoms. Prior to this, the universe was a hot, opaque plasma where light could not travel freely. The CMB is the first visible light that ever existed. Once neutral atoms formed, radiation could move through space without being absorbed or re-emitted. This moment, known as the decoupling of radiation, marked the point when the universe's first light began its journey through space. Over the next billions of years, as the universe expanded, the wavelengths of this radiation stretched, turning it into microwaves. Today, the CMB permeates the entire cosmos, with an average temperature of 2.725 Kelvin. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was one of the most important experimental confirmations of the Big Bang model. It demonstrated that the universe had a hot, dense origin, refuting the steady-state theory that proposed an eternal, unchanging universe. Since that groundbreaking discovery, several experiments have refined our understanding of the CMB. Satellites like COBE, Dewar-May-P, and more recently, Planck have mapped the small temperature fluctuations within the radiation with incredible precision. These fluctuations, on the order of 1 part in 100,000, are the seeds that would eventually grow into galaxies and other cosmic structures. Denser regions of the early universe attracted more matter over time, leading to the formation of galaxy clusters. Maps of the CMB reveal an almost uniform pattern, with tiny angular variations. These irregularities are crucial for understanding the physics of the early universe. They show that the universe wasn't perfectly homogeneous. Differences in density and temperature already existed. These slight discrepancies were essential for gravity to start forming structures. Without them, the universe would have been too uniform to form anything recognizable. The CMB also serves as a key tool for measuring cosmic distances and calibrating other cosmological phenomena by analyzing its spectrum and the acoustic oscillations it carries. By studying the CMB, cosmologists can determine fundamental parameters of the universe, including its age, the density of matter, and the ratio of dark matter to dark energy. Essentially, the CMB acts like a snapshot frozen in time, filled with vital information about the early universe. In addition to studying temperature variations, scientists also examine the polarization of the CMB. Polarization refers to the direction in which the electric fields associated with the radiation oscillate. This may reveal evidence of primordial gravitational waves, a prediction of cosmic inflation theory. Detecting these waves would allow scientists to peer even further back in time, possibly to the very instant when the universe began inflating. However, no definitive evidence of primordial gravitational waves has been found yet. An interesting feature of the CMB is the dipole, a temperature variation that indicates the motion of our Earth relative to the cosmic reference frame. This dipole shows that the universe has an isotropic background radiation, and any deviation we observe is due to our movement. By measuring this dipole, we can calculate the velocity of our solar system relative to the CMB, which is about 370 kilometers per second. Even though the CMB appears uniform, there are large-scale anomalies such as hemispherical asymmetries and unexpected cold spots. These irregularities are still being studied as potential signs of unknown phenomena. While they could just be statistical noise, some scientists have raised hypotheses about exotic events from the early universe. However, the data remains inconclusive, and these anomalies do not yet offer a solid explanation. The CMB also plays a crucial role in testing alternative cosmological models. Any theory that aims to replace or alter the Big Bang model must explain the existence, distribution, and spectrum of the CMB with at least the same level of precision. So far, the standard Big Bang model remains the most successful in explaining these observations. Looking to the future, missions like the LightBird satellite and ground-based telescopes, such as the Simons Observatory, are being prepared to detect B-mode polarizations in the CMB. These measurements require incredibly high sensitivity and could offer direct evidence of cosmic inflation. If such traces are detected, it would open a new window into the universe's first trillionth of a second, a time where the physics of the universe are still largely unknown. The CMB will continue to be an essential tool for probing the early universe, offering encoded information about the oldest events we can observe through light. By analyzing its features with greater precision, scientists will be able to refine cosmological models and test fundamental theories, helping us better understand the origin and evolution of the observable cosmos. Now let's explore the theory of cosmic inflation, the idea that the universe underwent an incredibly rapid expansion just after the Big Bang. This period of inflation is thought to have occurred between 10 circumflex 36 and 10 circumflex 32 seconds after the Big Bang. During this brief moment, the universe expanded exponentially, growing many times over in the blink of an eye. This expansion was faster than the speed of light, but it didn't violate the laws of relativity, because it was the space itself that was expanding. Einstein's theory of relativity prohibits objects with mass from moving faster than light, but it doesn't apply to the expansion of space. Inflation explains why the universe appears so homogeneous on large scales today. Regions that were once in contact were quickly separated by the rapid expansion. One of the main motivations for this theory was to solve the so-called horizon problem. Why do distant regions of the universe have nearly identical temperatures, even though they had no time to exchange energy? Inflation solves this by suggesting that these regions were once in contact before being separated by the rapid expansion. Inflation solved several key issues that were left unanswered by the standard Big Bang model, including the uniformity of the universe's initial properties. One of the major challenges inflation addresses is the flatness problem. Observations show that the universe is nearly perfectly flat, which would require extremely specific initial conditions. The rapid expansion during inflation smoothed out any curvature that might have been present at the start, making space appear nearly flat on large scales. This makes the geometry we see today a direct result of the inflationary process. Inflation also predicted the existence of tiny quantum fluctuations that were stretched by the rapid expansion. These fluctuations would later become the seeds for the galaxies, clusters, and filaments we see in the universe today. This concept connects quantum physics with the formation of large-scale structures in the cosmos. The variations we observe in the cosmic microwave background, CMB, match these predictions, providing further support for the validity of inflation. Inflationary theory was first proposed by Alan Guth in 1980 and refined by other scientists like Andre Linde. Over the years, different versions of inflation have been developed, including chaotic, hybrid, and slow-roll models, each suggesting different mechanisms for how inflation began and ended. However, all these models share the idea of rapid expansion and the generation of scale-dependent fluctuations. Current observations of the large-scale universe, particularly the CMB, align well with these inflationary models. Measurements like baryon acoustic oscillations, galaxy distributions, and the CMB spectrum all support the inflationary theory. Despite this, we still don't have direct evidence of inflation. Detecting primordial gravitational waves would be the game changer, offering a clear confirmation of inflation. These waves would leave a distinct signature in the polarization of the CMB. To detect such a signature, experiments like the BICEP-2 telescope and upcoming missions such as LIGHTBIRD and CMBS-4 are being developed. While the results so far haven't provided definitive proof, they have narrowed down the limits. The search for inflationary evidence continues to be one of the most exciting areas of observational cosmology, blending particle physics, gravity, and astrophysics into one unified field of study. However, inflation raises more questions than it answers. There are ongoing debates about how inflation began and ended. Some models propose highly specific initial conditions for inflation, while others suggest that inflation could occur naturally in fields with particular potentials. The nature of the inflationary trigger is still a topic of discussion. There's also no clear consensus about what happened immediately after inflation ended. While the standard model predicts a transition to a radiation-dominated universe, inflation still leaves us with several unresolved questions. One such question is the concept of eternal inflation. This idea suggests that inflation might continue forever in some parts of the universe, leading to a multiverse scenario where different regions of space-time have different physical laws. Although this idea is still debated, it remains beyond our ability to experimentally test. Even so, inflation continues to be the best model to explain the earliest moments of the universe, connecting quantum phenomena to the large-scale structure of the cosmos. Its theoretical framework is robust, and it offers an accurate explanation for many of the universe's observations. The search for direct evidence continues to guide the development of increasingly sensitive instruments. New observations will allow us to test these predictions more rigorously. Now let's explore the fascinating phenomenon of Hawking radiation and how black holes might eventually evaporate over time. Black holes are incredibly dense regions of space where gravity is so intense that not even light can escape. However, in 1974, physicist Stephen Hawking proposed a groundbreaking idea: black holes are not completely black. According to quantum mechanics, they can emit a faint form of radiation due to quantum effects near their event horizon. This emission, known as Hawking radiation, changed how we understand these extreme objects. The essence of Hawking's proposal is that quantum vacuum isn't truly empty. It's filled with pairs of virtual particles that appear and disappear. When this phenomenon occurs near a black hole's event horizon, one of these particles may be captured by the black hole's intense gravity, while the other escapes. To an external observer, this appears as radiation being emitted by the black hole. This process leads to the black hole losing energy over time, and since energy and mass are related by the famous equation E=mc², the black hole slowly loses mass. Over incredibly long timescales, this would eventually lead to the complete evaporation of the black hole. The rate of evaporation depends on the black hole's size. Larger black holes, like those with several times the mass of our Sun, would take longer to evaporate than the current age of the universe. But much smaller black holes, such as hypothetical primordial black holes, could evaporate much more quickly. Some physicists are exploring whether such objects might be emitting detectable bursts of radiation right now. So far, no direct evidence of Hawking radiation has been detected. The radiation is extremely faint, and for known astrophysical black holes, its intensity is too low to be observed with current technology. However, the theory aligns with the principles of both quantum physics and general relativity, and several analog experiments are underway to simulate similar phenomena in laboratory settings. Hawking radiation also introduces important questions about the conservation of information. If a black hole evaporates completely, what happens to all the information it contains? This issue is central to the so-called information paradox, which remains an unresolved mystery in theoretical physics. Various theories attempt to explain whether information is lost when a black hole evaporates, or whether it's encoded in the radiation or preserved in some unknown form. These debates have led to proposals for new models of quantum gravity, such as the idea of holography, or the theory that space-time is emergent. Another possibility is the existence of stable remnants of black holes after evaporation. These ideas aim to reconcile the conflict between quantum mechanics and general relativity, pushing toward a unified theory of physics. Some extensions of the Standard Model predict that microscopic black holes could be created in particle colliders if extra dimensions exist. Though this has never been observed, it remains a topic of theoretical research. At such small scales, Hawking radiation could have more noticeable effects, but this is still hypothetical. Current models involving compactified dimensions continue to be tested indirectly. Simulations are also being used to study how a black hole's evaporation affects the space-time around it. Some models suggest that the emission of radiation might slowly deform the black hole's event horizon, altering its thermal properties. These simulations provide more clues about the relationship between entropy, temperature, and gravity, furthering our understanding of the universe. While direct observations of Hawking radiation are still elusive, it remains one of the most fascinating predictions of combining quantum physics and general relativity. It offers a rare opportunity to study quantum effects in extreme gravitational fields. Although the phenomenon is still largely theoretical, its study remains at the forefront of modern physics, with many exciting questions yet to be answered. Finally, let's consider why certain parts of the universe will remain forever hidden from us. The observable universe is limited by the distance light has been able to travel since the Big Bang. Light travels at a finite speed, so we can only see objects whose radiation has had time to reach us in the 13.8 billion years since the universe began. This defines the horizon of the observable universe, which forms a sphere with a radius of about 46 billion light-years, taking into account the expansion of space itself. Even though the universe is 13.8 billion years old, the observable universe's radius is larger because space itself is expanding. As space stretches, galaxies move farther apart, and the light they emitted in the past continues to travel through this expanding space. This effect creates a dynamic observational boundary, meaning there are regions of the universe that have existed since the Big Bang, but their light hasn't had enough time to reach us yet. These areas lie beyond what we call the particle horizon. They may contain galaxies, structures, and phenomena, but they remain invisible to us due to the limits of light, which is our primary tool for observation. As time passes, the light from previously unreachable regions will eventually reach us, expanding the visible universe. But there are still regions that will forever be beyond our observational reach, and their light will never make it to us. This limitation doesn't mean these areas don't exist. It simply means we cannot observe them through light, and our view of the universe will always be constrained by the speed of light. The accelerated expansion of the universe driven by dark energy means that many regions will remain permanently invisible to us. While galaxies continue to emit light in our direction, the expansion stretches that light so much that it will never reach us. This means the visible universe is only a small fraction of the entire universe. What we see is not limited by technology, but by the fundamental constraints of physics. Any information from beyond this horizon is out of our reach, setting a natural boundary for observational cosmology. This influences the types of questions we can answer with direct data. The cosmic horizon also shapes how we interpret large-scale structures. Take the cosmic microwave background CMB, for example. It comes from a time when the universe was opaque, and beyond that, no light is directly observable. Even if there are structures past that point, their signals will never reach us. To study these boundaries, we rely on statistical inference, theoretical models, and extrapolation from known data. With advanced instruments like the James Webb Space Telescope and the upcoming Nancy Grace Roman Space Telescope, scientists are pushing the limits of our observable universe. These observatories will help us observe extremely distant galaxies, ones that emitted light when the universe was still a tiny fraction of its current age. These data are crucial for understanding the formation of the first structures and the early evolution of the cosmos. Despite these incredible capabilities, the limit imposed by the cosmic horizon remains unbreachable. The universe's accelerated expansion ensures that many regions will never become visible to us. Consequently, much of the universe will forever remain out of reach. This boundary not only affects what we can observe, but also how we interpret the uniformity and isotropy of the cosmos. To explore what lies beyond the visible universe, computational simulations model the behavior of space beyond the horizon based on the current distribution of matter and known physics. These models can help us estimate the continuity of cosmic structures on larger scales, although uncertainty increases the farther we go from the observable universe. The light horizon also has implications for theories like cosmic inflation and the multiverse. If different regions of the universe inflated independently, some may be permanently disconnected from ours, reinforcing the idea that there could be regions with distinct physical laws. While this notion is still debated, it remains outside the realm of experimental verification. Nonetheless, the limitations imposed by the horizon help shape the construction of more realistic models of the observable universe. The combination of observation, simulation, and theory continues to expand our knowledge of the universe we can access. Even within these defined limits, the cosmic calendar offers a way to conceptualize time in the vast scale of the cosmos. The cosmic calendar is a model that compresses the entire 13.8 billion years of the universe's history into a single calendar year, helping us put cosmic time into perspective. Each month represents just over 1.1 billion years, and each second represents about 438 years. This model makes it easier to comprehend the vast stretches of time involved in the universe's history. On this calendar, the Big Bang happens exactly at midnight on January 1st. The formation of the first stars and galaxies occurs between January and February, and the first large cosmic structures emerge throughout the first half of the year. By March, the Milky Way forms, and by September, our solar system comes into being. Earth forms around mid-September, and life begins in microscopic form soon after. For most of the year, the universe is dominated by simple life forms. Only in late December do complex life forms emerge. Dinosaurs appear on December 25th and go extinct on December 30th. All of recorded human history fits into the final moments of December 31st, with the Industrial Revolution occurring in the last seconds of the final minute. This scale puts human existence into a cosmic context, showing just how recent we are in the grand scheme of things. Even ancient events in human history, like the rise of civilizations, occupy only a tiny fraction of this model. Modern humans appear in the final 52 minutes of December 31st. Agriculture begins in the last 60 seconds, and all written history happens in the final 2 seconds. The cosmic calendar also serves as a tool to visualize the timing of natural processes. The formation of elements, the cooling of the universe, and the emergence of galaxies all occurred long before Earth was even habitable. This highlights the long time intervals between the birth of the universe and the conditions suitable for life. The cosmic calendar is a powerful teaching tool. It simplifies complex concepts, making the vastness of time more relatable. It is often used in books, documentaries, and science exhibits to help convey the enormity of the universe's history. While it simplifies many details, the calendar preserves the chronological order of events and helps compare astronomical and human scales. It's an accessible way to introduce concepts like deep time and cosmic evolution, bridging the gap between abstract numbers and human perception. As new data refine our understanding of the universe's age, the cosmic calendar can be adjusted to reflect the latest findings. These changes won't alter the calendar's overall function, but will provide a more accurate representation of the universe's timeline. The cosmic calendar is not just a symbolic model, but a tool grounded in real astronomical data and accepted by the scientific community. It connects cosmology, astrophysics, and paleontology, offering a comprehensive view of time that stretches from the Big Bang to the present and beyond. By combining this model with other timescales, such as Earth's geological time or future cosmic eras, we can create an even broader view of time. Comparing different scales reveals how various phenomena unfold at different rates. The cosmic calendar emphasizes these differences and highlights the importance of scale when interpreting astronomical data. As observational data improves, models like the cosmic calendar will continue to be invaluable for both scientific communication and educational exploration. The cosmic calendar is just one way to help us understand the universe's past, but it remains an essential tool for expanding our comprehension of cosmic evolution and the events that have shaped the observable universe. The search for new discoveries like gravitational waves continues to expand our view of the cosmos, offering new insights into the universe's origins and future. Speaking of which, let's turn our attention to gravitational waves, the ripples in space-time caused by the motion of massive objects. These waves were first predicted by Einstein in 1916, and for decades they remained purely theoretical. That was until 2015, when the LIGO experiment detected them for the first time. The detection of gravitational waves from the merger of two black holes, about 1.3 billion light-years away, confirmed their existence. Since then, gravitational wave astronomy has taken off. In 2017, the LIGO and Virgo detectors recorded the collision of neutron stars, a discovery that brought even more exciting results. For the first time, scientists observed both gravitational waves and light from the same cosmic event. Neutron stars are incredibly dense remnants of supernovae. When two of them collide, they release an immense amount of energy, producing a burst of radiation that's billions of times more intense than the sun's light. This collision also creates heavy elements like gold and platinum, which are spread throughout the universe, becoming part of future stars and planets. The detection of gravitational waves from neutron star collisions has provided a wealth of new information, including how gravitational waves travel at the speed of light, and how the collision produced a kilonova, a type of supernova explosion rich in heavy elements. This discovery has opened a new chapter in astronomy, known as multi-messenger astronomy, where gravitational waves and light are detected simultaneously, offering a more complete picture of cosmic events. The study of gravitational waves offers a unique opportunity to investigate processes occurring in extreme environments, such as intense gravitational fields and densities that we cannot replicate in laboratories. Detectors like LIGO, Virgo, and CAGRA use incredibly sensitive lasers to measure the smallest variations in distance between mirrors. Gravitational waves distort space so subtly that the changes are smaller than the diameter of a proton. This level of precision demands carefully controlled environments, seismic isolation, and complex computational techniques to filter out noise from the signal. Each new detection helps refine our understanding of binary system formation, neutron star structure, and the boundaries of nuclear physics. Some observations suggest that black hole and neutron star collisions also occur, producing unique signatures. These events are harder to detect but provide invaluable data on matter under extreme pressure. In addition to helping us understand cosmic events, gravitational waves can also serve as a cosmic ruler to measure distances in the universe. Events like GW 170817 have enabled scientists to accurately estimate the Hubble constant, which describes the rate at which the universe is expanding. Comparing these values with other methods helps clarify discrepancies in current measurements, making gravitational waves an important tool in precision cosmology. Looking ahead, space missions such as the LASER Observatory, slated for launch in the 2030s, will aim to detect lower-frequency gravitational waves. This will allow scientists to observe supermassive black hole mergers and trace the history of galaxy formation. These future observations will complement data from ground-based detectors and expand our reach to even more distant scales. Computational models play a crucial role in predicting the waveforms produced by different types of collisions. Each event creates a unique pattern that can be identified within large datasets. By comparing detected signals with these models, scientists can infer properties like the masses, spins, and compositions of the objects involved. This requires close collaboration between theoretical physicists, engineers, and astronomers. The field of gravitational waves is still in its infancy but is advancing rapidly, and with each observation cycle, the chances of detecting rare, unexpected phenomena grow. Integrating gravitational wave data with optical, infrared, and gamma-ray observations enriches our understanding of cosmic events. With expanding detection networks, we anticipate a significant increase in the number of identified events in the coming years. Now let's shift focus to event horizons, the boundary around black holes beyond which nothing, not even light, can escape. The event horizon marks the point at which the escape velocity exceeds the speed of light. According to general relativity, space-time curves so intensely at this radius that all possible paths for a particle inevitably lead inward. The event horizon isn't a physical surface, but a mathematical boundary that defines the point of no return. The distance from the center of a non-rotating black hole to its event horizon is called the Schwarzschild radius. This radius depends solely on the black hole's mass and increases as the mass grows. For example, a black hole with the mass of the Sun would have an event horizon about 3 kilometers wide, while supermassive black holes, like the one at the center of the Milky Way, can have event horizons spanning millions of kilometers. Once an object crosses the event horizon, it becomes causally disconnected from the rest of the universe. From an outside observer's perspective, the object appears to freeze as it approaches the horizon due to gravitational time dilation. As it nears the event horizon, the light emitted from it becomes increasingly redshifted and eventually becomes undetectable. However, from the object's own perspective, it crosses the event horizon without experiencing anything unusual at that exact moment. The event horizon is crucial for understanding the nature of black holes. It is where both general relativity and quantum theory must be considered. The physics near the event horizon is still a topic of active research, especially as scientists attempt to reconcile these two principles. Quantum effects near the event horizon have led to predictions like Hawking radiation, which suggests that black holes can gradually lose mass over time. In rotating or charged black holes, the area around the horizon becomes more complex. These black holes have inner and outer event horizons as well as an ergosphere, where space-time is dragged in the direction of the black hole's rotation. In these cases, particles can gain energy by entering the ergosphere and escaping, a process known as the Penrose process. These phenomena have significant implications for high-energy astrophysical environments. Event horizons also represent the limits of observational astronomy. Since no light can escape from within them, direct information from inside a black hole is fundamentally inaccessible. Instead, astronomers rely on indirect evidence such as the motion of nearby objects, gravitational lensing, and radiation from accretion disks to confirm the presence and properties of event horizons. Numerical simulations help us understand the stability of black holes in general relativity. These simulations track the formation and evolution of black holes during stellar collapse or mergers and predict gravitational waves, high-energy emissions, and relativistic jets associated with the regions just outside the event horizon. Horizon thermodynamics is another exciting area of research. The event horizon can be assigned properties like entropy and temperature, forming the foundation of black hole thermodynamics. The entropy is proportional to the surface area of the horizon, not its volume, which has led to the development of the holographic principle in theoretical physics. Although still under investigation, these ideas suggest deep connections between quantum mechanics, information theory, and gravity. The event horizon serves as a testing ground for fundamental principles, such as the cosmic censorship conjecture, which proposes that singularities, points of infinite curvature, are always hidden within event horizons and never visible to external observers. While consistent with observations so far, this remains an open question in general relativity. Event horizons are central to discussions on black hole stability and evolution. They provide key insights into accretion processes, energy output, and relativistic effects near compact objects. Understanding their behavior is essential for interpreting data from radio, X-ray, and gravitational wave astronomy. Advanced models like the Kerr-Newman and Reissner-Nordström solutions are used to describe event horizons in rotating and charged black holes. These models predict unique structures and interactions near the horizon, shaping our understanding of extreme gravity. By refining these equations, we can better align theoretical predictions with the data collected by modern observatories and gravitational wave detectors. Although event horizons cannot be directly observed, their effects on nearby matter and radiation give us several ways to study them. They define the boundaries of accessible space-time and remain essential features of astrophysical black holes in both theory and observation. Moving forward, let's discuss the remarkable achievement of capturing the first image of a black hole, the supermassive black hole at the center of the galaxy. Messier 87, Messier 87, was the target of the first successful attempt to directly image a black hole's shadow. In April 2019, the Event Horizon Telescope (EHT) collaboration unveiled this historic image, marking a major milestone in observational astronomy. The image revealed a ring-like structure caused by light bending around the black hole's event horizon. With a mass 6.5 billion times that of the Sun, M87's black hole is located about 55 million light-years from Earth, surrounded by a bright accretion disk of infiling gas and dust. As matter spirals inward, it heats up to extreme temperatures, emitting electromagnetic radiation, especially in the radio spectrum. The intense gravity of the black hole bends and distorts this radiation, forming a shadow-like region in the center. The EHT, an array of radio observatories across the globe, used a technique called Very Long Baseline Interferometry, VLBI, to synchronize observations and combine data, effectively creating a telescope the size of Earth. This allowed astronomers to resolve the black hole's event horizon for the first time. The observed ring is not a direct image of the black hole itself, but of the photon ring, the path traced by light that orbits the black hole due to extreme gravitational lensing. The dark region at the center represents the shadow where light paths are bent inward and absorbed. This structure aligns with predictions from general relativity and offers strong evidence supporting Einstein's equations under extreme conditions. The imaging process involved analyzing petabytes of data collected over several nights, with sophisticated algorithms reconstructing the image by examining light delays and interference patterns. Independent teams processed the data to ensure consistency, confirming the breakthrough in black hole observation. The image of MED7's black hole revealed a ring with asymmetrical brightness caused by relativistic effects like Doppler beaming on the side of the accretion disk rotating toward us. This was not just a technical achievement, but also a critical test of theoretical predictions. The size and shape of the shadow perfectly matched what was expected from a rotating black hole or a Kerr black hole. No deviations from general relativity were observed at the resolution scale that was available. Future observations are expected to refine these measurements further and detect even subtler features like polarization patterns or time variability. The successful imaging of M87 confirmed that black holes can be studied through their interaction with surrounding matter. It demonstrated that resolving structures near the event horizon of galaxies beyond our own is not only possible, but feasible. This sets the stage for future observations of other black holes, including Sagittarius Arastris, the supermassive black hole at the center of the Milky Way. The result also offered new insights into the dynamics of accretion disks and the formation of relativistic jets. M87, for example, is known for emitting a powerful jet that extends thousands of light-years into intergalactic space. Understanding how matter behaves near the event horizon will help us understand jet formation, angular momentum transfer, and magnetic field alignment in these extreme environments. The Event Horizon Telescope (EHT) continues to expand its capabilities by incorporating more observatories and improving sensitivity. Planned upgrades will allow for time-resolved imaging, enabling scientists to track changes in the disk and jet over time. These dynamic observations could provide an even more precise understanding of black holes, transforming them into active astrophysical laboratories. The success of M87's imaging highlights the power of combining theory, engineering, and computational science, showing how global collaboration can overcome the limitations of individual instruments and produce results that test the laws of physics in extreme conditions. The data also contribute to models of galaxy evolution and supermassive black hole growth. Further studies of black holes will improve our knowledge of their mass, spin, and magnetic fields. As more black holes become observable, comparative studies across different environments may uncover patterns or anomalies that current theories cannot yet explain. The image of M87's black hole has set a new benchmark for high-resolution radio astronomy, proving that it is possible to capture images of objects at the heart of galaxies millions of light-years away. Now, let's dive into supernova 1987A, one of the most significant astronomical events of the 20th century. This supernova, which occurred in the Large Magellanic Cloud, a nearby satellite galaxy of the Milky Way, was visible to the naked eye on February 23, 1987, making it the closest supernova to Earth since the invention of the telescope. Its proximity gave astronomers an unprecedented opportunity to study the details of a core collapse supernova. But supernova 1987A wasn't a typical supernova. It exhibited several anomalies that challenged existing models. One of the most striking features was the asymmetry of the explosion. Unlike a typical spherical explosion, the debris from SN 1987A showed a clear directional preference, forming elongated structures and multiple rings. This pointed to a more complex internal dynamic during the star's collapse and explosion. The progenitor star, a blue supergiant named Sanjul X 69°202, was not what scientists had expected. Standard models predicted that Type II supernovae should come from red supergiants, not blue ones. The presence of this blue supergiant suggested differences in the star's internal structure, rotation, or metallicity that influenced its evolution. The star's compact size and higher temperature might have contributed to the asymmetry observed in the collapse. Neutrino detectors on Earth, including CAMEO and IMB, recorded a burst of neutrinos just before the visible explosion. This confirmed theoretical predictions that most of the energy released in a supernova is emitted as neutrinos. This detection provided the first direct evidence of the inner mechanisms of a collapsing star and validated models of neutron star formation. The timing and energy distribution of the neutrinos matched core collapse expectations. As the outer layers of the star were expelled, they collided with surrounding material previously displaced by the star during earlier stages of its life. This interaction created shock waves and formed the iconic triple ring structure seen in Hubble Space Telescope images. These rings are composed of glowing gas that was illuminated by the shock front. Studying their motion and composition has provided valuable insights into the star's pre-supernova mass loss and internal dynamics. The asymmetry in SN 1987A is thought to have been caused by instabilities in the core during collapse. Models suggest that convection, turbulence, and rotation within the core can distort the shock wave, leading to an uneven ejection of material. In some simulations, jets or plumes form preferentially along certain axes. These directional effects can influence both the distribution of heavy elements and the velocity of the resulting neutron star. Ongoing observations continue to track the expansion of the supernova remnant. The inner region remains obscured by dust, but data from X-ray and infrared telescopes are gradually revealing the dense core. Some evidence suggests that a neutron star may have formed, although this has not yet been confirmed. The unique conditions of SN 1987A have made it a critical benchmark for supernova modeling. It forced revisions to theories about progenitor stars, explosion mechanisms, and post-supernova evolution. The detailed observational record across neutrinos, light, and various wavelengths provides a rare opportunity to calibrate simulations against real data. These insights are being used to refine predictions for future nearby supernova. As SN 1987A continues to evolve, the rings surrounding it are brightening and changing shape, offering a dynamic view of how supernova remnants interact with their circumstellar environments. This has broader implications for understanding how supernova enrich the interstellar medium with heavy elements and influence star formation in galaxies. SN 1987A has also underscored the importance of multi-wavelength observation strategies. Its study involved radio, optical, ultraviolet, X-ray, and neutrino data, demonstrating how different physical processes become visible at different wavelengths. This approach has since become standard in transient astronomy, guiding instrument design and data interpretation. Future observations with more sensitive instruments like the James Webb Space Telescope and next-generation X-ray observatories may resolve lingering questions about the compact object left behind in SN 1987A. If a neutron star is found, it could offer new insights into matter at nuclear densities and the aftermath of asymmetric explosions. SN 1987A remains one of the richest scientific events in the field of observational astrophysics. Now let's talk about neutron stars. How a teaspoon of neutron star material can weigh billions of tons. Neutron stars are the incredibly dense remnants of massive stars that have exploded in supernovae. After the outer layers are expelled, the core collapses under gravity, compressing protons and electrons into neutrons. The result is an object with a radius of about 10 to 12 kilometers, but a mass greater than that of the Sun. A single cubic centimeter of neutron star material weighs more than a mountain. In fact, a teaspoon of neutron star material would weigh about 5 billion tons on Earth. This extreme density means that the matter inside a neutron star is in a degenerate quantum state, with neutrons packed closely together. The physics governing this state is described by the nuclear equation of state, which is still an active area of research. Neutron stars also have incredibly strong surface gravity, about 100 billion times stronger than Earth's. A fall of just 1 meter would result in an impact equivalent to hitting a solid wall at nearly the speed of light. Some neutron stars also have intense magnetic fields, often 1 trillion times stronger than Earth's. These magnetic fields can drive high-energy emissions and regulate plasma behavior around the star. Some neutron stars rotate incredibly rapidly, completing hundreds of rotations per second. These rapidly spinning neutron stars are called pulsars. They emit beams of electromagnetic radiation from their magnetic poles, and when these beams sweep past Earth, we observe them as pulses of light. Pulsars are some of the most accurate cosmic clocks we have, allowing scientists to study general relativity, test gravitational waves, and probe interstellar space. Neutron stars provide a natural laboratory for studying matter under extreme conditions. Their interiors may contain more exotic particles like hyperons or deconfined quark matter. At the core, densities could be high enough for quarks to exist freely, forming a quark-gluon plasma. Detecting these states requires indirect methods, such as analyzing the mass and radius of neutron stars or studying merger events. Neutron star mergers, detected through gravitational waves, offer unique opportunities to explore their internal composition. The waveform and electromagnetic counterparts of these events depend on the star's stiffness and their response to tidal forces. Data from LIGO, Virgo, and other observatories are used to constrain the nuclear equation of state. Isolated neutron stars can cool over time, and studying their thermal emissions helps us understand how superfluid and superconducting states behave in dense matter. X-ray telescopes like ANISA and Chandra map temperature distributions and infer the surface composition of these stars. These observations contribute to our understanding of particle interactions in environments we cannot replicate on Earth. Some neutron stars exhibit sudden changes in their rotation rates, known as glitches. These are thought to occur due to shifts in the star's internal structure, such as interactions between its solid crust and superfluid core. Studying these glitches provides valuable insight into the properties of ultra-dense matter and the mechanics of angular momentum transfer at nuclear densities. Magnetars are a subclass of neutron stars that possess extremely powerful magnetic fields. These fields can twist and snap, releasing massive amounts of energy in the form of X-ray and gamma-ray bursts. Magnetars are thought to be responsible for certain fast radio bursts and soft gamma repeaters, making them key targets for multi-messenger and time-domain astronomy. In binary systems, accretion-powered neutron stars attract material from companion stars. As this material spirals inward, it forms an accretion disk that emits X-rays. The transfer of mass and angular momentum leads to complex observational signatures, such as pulsations, thermonuclear bursts, and spectral lines, which allow scientists to measure magnetic field strength and surface gravity. Although neutron stars are only a few kilometers in diameter, their influence stretches far beyond their physical boundaries. They shape the surrounding space through gravity, radiation, and magnetic fields. By studying these compact objects, we gain insight into supernova mechanisms, nucleosynthesis, and the life cycles of massive stars. Future observations with next-generation X-ray and gravitational wave observatories will refine our understanding of neutron stars' mass, radius, and internal composition. These data will improve theoretical models and may uncover previously unknown phases of matter. Neutron stars will remain central to high-energy astrophysics and fundamental physics research. Now let's turn to quasars, ancient galaxies with ultra-energetic cores. Quasars, or quasi-stellar objects, are extremely luminous cores of distant galaxies powered by supermassive black holes. These objects are among the brightest in the universe, capable of outshining their entire host galaxies. A typical quasar emits hundreds to thousands of times more energy than the Milky Way, all from a region only a few light days across. Quasars were first identified in the 1960s due to their strong radio emissions and high redshifts. At the center of a quasar lies a supermassive black hole, surrounded by an accretion disk of gas and dust. As this material spirals inward, it heats up due to friction and gravitational compression, reaching temperatures of millions of degrees. This process results in intense radiation across the electromagnetic spectrum, from radio waves to X-rays. The most powerful quasars are found at high redshifts, meaning their light has traveled billions of years before reaching Earth. This indicates that quasars were more common in the early universe, especially between 1 and 3 billion years after the Big Bang, when galactic mergers were frequent and fueled active galactic nuclei. Over time, as fuel became scarce, many quasars faded into dormancy. Spectroscopic studies of quasars show broad emission lines produced by ionized gas moving at high velocities near the black hole. These lines allow astronomers to measure redshifts, estimate distances, and analyze the composition and velocity of the material around the quasar. Some quasars also exhibit outflows or jets, relativistic streams of charged particles expelled from the black hole's poles, shaped by strong magnetic fields. These jets can be observed across vast distances and help us study the physics of relativistic jets. Quasars also act as probes of the intergalactic medium. As their light passes through intervening gas clouds, it gets partially absorbed at specific wavelengths, creating absorption lines. By studying these features, scientists can map the distribution of matter between galaxies and track the chemical evolution of the universe. This has been crucial for understanding the large-scale structure of the cosmos, including the formation of cosmic filaments and voids. Certain quasars display variability in brightness over timescales ranging from days to years. These fluctuations arise from changes in the accretion rate, instabilities in the disk, or gravitational lensing effects. Monitoring these variations helps scientists infer the physical conditions near the black hole and test models of accretion physics in extreme gravity. The most energetic quasars, known as blazars, have relativistic jets that are oriented directly toward Earth. This alignment causes strong Doppler boosting, making the quasar appear even brighter and more variable. Blazars are prime targets for high-energy observatories because they emit gamma rays and exhibit rapid changes in intensity. These features make them ideal for studying jet formation and testing relativistic jet physics. Surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Spectroscopic Instrument, DSI, have catalogued hundreds of thousands of quasars, enabling statistical studies of their distribution and evolution. These data show that quasar activity peaked early in the universe's history, declining as galaxies matured and their central black holes exhausted their fuel supply. Quasars are also important for understanding galaxy formation. The energy they release can heat or expel gas from the host galaxy, suppressing star formation and regulating galactic growth. This feedback mechanism is essential in simulations of galaxy evolution, helping to explain observed correlations between black hole mass and galaxy bulge properties. The rapid formation of supermassive black holes in the early universe remains an intriguing mystery. Some theories propose that these black holes formed through the direct collapse of massive gas clouds, bypassing the usual stellar evolution process. Others suggest that they grew rapidly through mergers and sustained accretion. Ongoing observations aim to clarify which processes dominated in the early universe. In the future, instruments like the James Webb Space Telescope and the Extremely Large Telescope will provide high-resolution data on early quasars, revealing details about their host galaxies, environments, and black hole properties. These observations will deepen our understanding of how the first luminous structures shaped the universe we see today. Finally, let's consider the Lernia supercluster and our position within the cosmic web. The Lernia supercluster is a vast structure encompassing over 100,000 galaxies, including our own Milky Way. The name Lernia means immense heaven in Hawaiian, which reflects the immense scale of this gravitationally bound region. First identified in 2014 by Brent Tully's team, Lernia spans about 520 million light-years and includes several previously known clusters, such as the Virgo and Hydra Centaurus superclusters. Superclusters are not isolated objects. They are part of the larger cosmic web, a network made up of filaments, nodes, and voids formed by the gravitational collapse of matter over billions of years. Galaxies tend to cluster along these filaments, with superclusters occupying the densest regions. Lernia represents one of these nodes, defined by the flow of galaxies within its gravitational influence. The identification of Lernia was based on mapping the peculiar velocities of galaxies, their motions after accounting for the Hubble expansion. These motions reveal gravitational attractors and repellers that shape the large-scale distribution of matter. By analyzing the flow of galaxies toward a common center, researchers were able to map the boundaries of the supercluster and estimate its total mass to be around 10 circumflex 17 solar masses. At the center of Lernia lies the Great Attractor, a gravitational anomaly that influences the motion of galaxies in our region of the universe. The Milky Way and its neighboring galaxies are moving toward this region at hundreds of kilometers per second. Though obscured by the plane of our galaxy, the Great Attractor is believed to consist of dense concentrations of galaxy clusters and dark matter. Lernia is not a gravitationally bound object in the long term. due to the accelerating expansion of the universe caused by dark energy. The outer regions of Lanya will eventually move beyond our cosmic horizon. Nonetheless, within its current scale, Lanya provides a valuable reference point for understanding the local structure of the universe and our place in it. The distribution of galaxies within Lanya reflects the underlying distribution of dark matter. These models accurately replicate features like superclusters, cluster mergers, and the cosmic connectivity we observe. Lanya fits seamlessly into this framework as one of the many superstructures shaping the observable universe. The galactic flows within Lanya also provide data that help refine cosmological parameters. By comparing the observed motion of galaxies to predictions from the Lambda CDM model, scientists can test assumptions about dark energy, matter density, and the universe's initial conditions. This comparison plays a crucial role in refining our understanding of the origin and evolution of cosmic structures. Efforts to map the boundaries and substructures of Lanya continue. Projects like Cosmic Flows and future missions with deeper redshift surveys aim to enhance distance measurements and improve flow reconstructions. These efforts contribute to a clearer understanding of the local universe and its connection to the broader cosmic web. The study of Lanya emphasizes the importance of scale in cosmology. While galaxies and clusters are familiar objects, superclusters like Lanya represent the fundamental architecture of matter on the largest observable scales. By understanding the formation, dynamics, and limits of these structures, we gain context for our position in the universe, shaping models of cosmic structure formation. Moving on to a different aspect of cosmic mystery, the Fermi paradox. Why haven't we found intelligent life elsewhere in the universe? The paradox is built on a simple but profound question. If intelligent life is common in the cosmos, why haven't we found any evidence of it? Given the sheer number of stars and potentially habitable planets, it seems logical to assume that advanced civilizations should have emerged, developed technology, and left detectable traces. Yet, despite decades of searching through programs like SETI, no confirmed signals or artifacts have been found. Enrico Fermi famously raised this paradox in 1950, asking, "Where is everybody?" The contradiction between the high probability of extraterrestrial life and the lack of any evidence remains unresolved. Modern estimates, like the Drake equation, try to quantify the number of communicative civilizations, but they depend on uncertain factors, ranging from stellar formation rates to the lifespan of civilizations. One possible explanation is that intelligent life is incredibly rare, or perhaps Earth is unique. This could be due to a series of improbable events, like the origin of life, the emergence of intelligence, or the transition to technological societies, all of which may make the rise of complex life extraordinarily unlikely. Others speculate that civilizations may self-destruct before they reach the stage of becoming spacefaring due to war, resource depletion, or artificial intelligence gone awry. Some hypotheses suggest that extraterrestrial life exists, but intentionally avoids contact. This zoo hypothesis proposes that advanced species are simply observing us, waiting for us to reach a certain level of development. Alternatively, extraterrestrials might communicate in ways we can't detect yet, perhaps using quantum entanglement, neutrinos, or technologies far beyond our current understanding. Our instruments may be too primitive to pick up these signals. Another possibility is that civilizations rise and fall at different points in cosmic time, with little overlap. The universe is over 13 billion years old, so even if a civilization existed for just 1,000,000 years, it would be a mere flash in the grand timeline of the universe. The probability of overlapping with such a civilization, let alone detecting it, may be much lower than we think. We could be early, late, or simply isolated in time and space. Some researchers suggest that intelligent civilizations avoid broadcasting signals to reduce the risk of detection by hostile species. This idea is known as the dark forest hypothesis, which views the universe as a place where silence is key to survival. In this scenario, the absence of signals doesn't mean the absence of life, it's simply a matter of collective caution. The search for techno-signatures is expanding beyond just radio signals. New strategies now include searching for signs of industrial pollution in exoplanet atmospheres, waste heat from megastructures or laser pulses, Space telescopes like the James Webb Space Telescope, JWST, and ground-based surveys are becoming increasingly sensitive to anomalies that could point to artificial origins. However, no confirmed detections have emerged so far. Another avenue of research asks whether our assumptions about life are too Earth-centric. Life might exist in forms that don't rely on carbon chemistry, liquid water, or familiar biology. If that's the case, we may be missing signs of intelligence simply because we're looking for the wrong clues. Astrobiology is gradually expanding its definition of habitability and intelligence. The Fermi paradox also prompts debates in evolutionary biology, sociology, and the philosophy of science. It challenges our assumptions about intelligence, civilization, and progress, forcing us to reconsider what we understand about life on a cosmic scale. These discussions highlight the limitations of thinking only within the framework of Earth-like life. Despite the lack of contact, the search for extraterrestrial intelligence continues to thrive. Scientific missions are mapping exoplanets, searching for biosignatures, and developing more powerful instruments to scan the sky. Each non-detection refines our models, narrowing the parameter space. For now, the paradox remains unresolved, not because we have no answers, but because we have many, each filled with uncertainty. Next, let's talk about Dyson spheres, hypothetical megastructures designed to capture a star's energy. First proposed by physicist Freeman Dyson in 1960, a Dyson sphere isn't a solid shell around a star, but rather a swarm of satellites or solar collectors orbiting it. The idea comes from the fact that, as a civilization grows, its energy demands might exceed what a planet can supply, pushing them to look for ways to harness stellar energy. Dyson's concept suggests that any sufficiently advanced civilization would eventually exploit its star's energy. These structures would emit waste heat in the infrared spectrum, making them potentially detectable from far away. Modern SETI programs have used infrared surveys like those from the WISE telescope to search for unusual sources of heat that could suggest Dyson-like structures. However, a complete Dyson sphere would require an enormous amount of material, far more than Earth alone could provide. Some variants, like Dyson swarms or Dyson bubbles, involves independent satellites orbiting the star in intricate patterns, reducing the engineering challenge. These structures could be built incrementally, offering flexibility and redundancy, but they remain far beyond our current technological capabilities. If a civilization could construct a Dyson sphere, it would have reached Type 2 on the Kardashev scale, a system that classifies civilizations by their energy usage. Earth's civilization is currently at Type 0.7. A Type 2 civilization would harness the entire energy output of its star, around 10 circumflex 26 watts, enabling megaprojects and possibly even interstellar expansion. Theoretical discussions also include more speculative versions of Dyson structures, such as Matryoshka brains, nested Dyson shells, used to power massive computational systems. These ideas extend the concept beyond energy harvesting to advanced computing, artificial intelligence, and long-term survival strategies. While Dyson spheres remain purely theoretical, they provide a useful framework for thinking about how advanced civilizations might evolve. Detecting Dyson spheres relies on indirect methods, as a complete sphere would block visible light and emit it as infrared radiation. Astronomers have scanned for such signals but haven't found conclusive evidence yet. Some candidates, like the star KIC 8462852, have emerged, but subsequent observations favored natural explanations such as dust clouds or comet swarms. Building a Dyson structure would require solving extreme engineering challenges such as orbital stability, material strength, and collision avoidance. Despite these challenges, Dyson spheres remain a powerful theoretical tool for studying the evolution of advanced civilizations. If civilizations continue to develop technologically, some might eventually alter their stars in detectable ways. The absence of such evidence ties back to the Fermi paradox and shapes our expectations about cosmic engineering. Future missions like the Nancy Grace Roman Space Telescope or next-generation infrared observatories may help detect fainter or more distant Dyson-like structures. As our observational capabilities improve, the search for megastructures will become more refined. Dyson spheres may remain a conceptual tool, but they play a significant role in astrobiology and technosignature research. bridging the gap between astrophysics, engineering, and the search for extraterrestrial intelligence. When exploring planets around red dwarfs, scientists face unique challenges. These stars emit intense radiation, including ultraviolet and X-ray flares, which can gradually erode planetary atmospheres. Over time, repeated flare events might strip away protective layers like ozone, leaving planets vulnerable to harmful radiation. Such radiation levels make it difficult to sustain the stable environmental conditions needed for life, even within what we traditionally consider the habitable zone. However, some models suggest that certain planetary features could provide a buffer. Planets with strong magnetic fields could deflect charged particles, while thick atmospheres might shield the surface from harmful radiation. Oceans, or subsurface environments, also offer potential sanctuaries where microbial life could endure despite harsh surface conditions. Among the closest potentially habitable planets to Earth are those orbiting red dwarfs. Proxima Centauri b, located just over 4 light-years away, is one such example. Though it lies within its star's habitable zone, the frequent flares raise questions about its ability to retain an atmosphere. Similarly, the TRAPPIST-1 system, with its 7 Earth-sized planets, has several planets in the habitable zone, but they likely face similar challenges due to their star's flaring activity. The study of exoplanets around red dwarfs is rapidly advancing, with instruments like the James Webb Space Telescope playing a crucial role. Using transit spectroscopy, scientists aim to identify key atmospheric components, such as water vapor and carbon dioxide, which could indicate potential for life. But the frequent stellar flares complicate observations, requiring extensive data collection over several transits to ensure accuracy. The dynamic nature of red dwarf stars requires a rethinking of traditional habitability models. To assess the potential for life, researchers propose new metrics that incorporate factors like stellar flare frequency, magnetic field strength, and atmospheric erosion rates. Such factors will help scientists refine the habitable zone concept and provide a more comprehensive understanding of what constitutes a life-supporting environment. Red dwarfs have incredibly long lifespans, sometimes lasting trillions of years. This provides an extended period during which planets could develop life. While early conditions may be harsh, the later stages of a red dwarf's evolution could offer more stable conditions. This means that life could potentially emerge or re-emerge after prolonged periods of stellar activity, expanding our understanding of where life might thrive. Interestingly, red dwarfs also challenge our current understanding of planetary formation. These stars often have cooler, lower-mass protostellar disks, which might seem like a disadvantage for planet formation. Yet, observations show that Earth-sized planets are quite common around these stars, suggesting that efficient formation mechanisms operate even under less than ideal conditions. The sheer number of red dwarfs in our galaxy underscores their importance in the search for habitable planets. Even if only a small fraction of planets around these stars are suitable for life, the large number of red dwarfs means that many habitable worlds could still exist. Therefore, despite the challenges these stars pose to habitability, they remain a critical area of focus for astronomers. As technology advances, future missions like the Extremely Large Telescope and other space-based observatories will provide deeper insights into planets orbiting red dwarfs. With better sensitivity and higher resolution, researchers will be able to identify planets that retain stable atmospheres, support climates conducive to life, and in the best case, harbor life forms. When considering the habitable zone, a region around a star where liquid water could exist on a planet's surface, it's clear that this traditional model is too simple. While distance from the star is important, it's far from the only factor determining a planet's habitability. Atmospheric composition, planetary mass, and geological activity are also critical components. For instance, a planet too close to its star could suffer a runaway greenhouse effect, similar to Venus, while one too far might have its water frozen into ice unless other factors, like internal heating or a thick atmosphere, compensate. The composition of a planet's atmosphere plays a key role in maintaining liquid water. Greenhouse gases such as carbon dioxide and methane can warm the planet, while clouds and aerosols might cause cooling. The right balance is necessary for liquid water to exist over geological timescales. Planetary mass also impacts habitability. Smaller planets may struggle to retain their atmospheres, especially if they experience high stellar radiation. Without enough gravity, their atmospheres can escape into space. Larger planets might hold onto thick atmospheres, but may have toxic chemical conditions or high surface pressures. Striking the right balance is essential for maintaining a stable climate. Geological activity is another crucial factor in determining a planet's habitability. Mechanisms like plate tectonics and volcanic activity regulate the planet's atmosphere, helping stabilize temperatures over long periods. A planet without geological activity might not recycle carbon or protect its atmosphere, reducing its potential for long-term habitability, even if it lies in the traditional habitable zone. The characteristics of the host star also affect a planet's ability to support life. Younger stars tend to emit more flares and ultraviolet radiation, while older stars may become more luminous over time, potentially shifting a planet out of the habitable zone. Understanding a star's life cycle is essential for predicting long-term habitability. Subsurface environments provide another avenue for habitability. Moons like Europa and Enceladus, which harbor liquid oceans beneath their icy surfaces, demonstrate that life could potentially exist in environments not dependent on stellar radiation. In such cases, internal heat sources may be enough to support liquid water, even in the absence of sunlight. Tidal locking, a situation where a planet always shows the same face to its star, presents another challenge. This could create extreme temperature differences between the day and night sides of the planet. However, models suggest that thick atmospheres or large oceans could redistribute heat, maintaining stable conditions across a broader region of the planet. The search for life beyond Earth continues to rely on instruments like the James Webb Space Telescope, which is designed to detect biosignatures in exoplanet atmospheres. While detecting such signatures is challenging, the absence of certain chemicals, like oxygen or methane, doesn't rule out the presence of life. Rather, it highlights the difficulty in identifying life across vast distances. The habitable zone remains a useful tool in the search for life, but it is only the starting point. Ongoing research aims to refine this concept by incorporating planetary, stellar, and atmospheric complexity. These refinements will help focus the search on the most promising candidates for life beyond Earth. Take the TRAPPIST-1 system, for example. This system, located about 40 light-years from Earth, consists of 7 Earth-sized planets, 3 of which are in the traditional habitable zone. These planets orbit very close to their star, TRAPPIST-1, but its low luminosity allows some of them to remain within the habitable zone, where liquid water could exist. The proximity of these planets to their star results in short orbital periods, making them ideal for repeated observation. The planets in the TRAPPIST-1 system regularly pass in front of their star, allowing astronomers to study their atmospheres using transit spectroscopy. Instruments like the James Webb Space Telescope are expected to detect gases such as water vapor, carbon dioxide, and methane, which could suggest habitability. However, the system's proximity to its star also raises concerns about tidal locking and the impact of stellar flares. Still, the potential for discovering habitable worlds in this system is incredibly promising, making it a key target in the search for life beyond Earth. Some climate models suggest that habitable regions might still exist along the terminator line, the twilight zone between a planet's day and night sides. This zone could provide more stable conditions despite the challenges posed by stellar flares. These flares, particularly ultraviolet and X-ray radiation, can strip away a planet's atmosphere, especially if the planet lacks a magnetic field. However, planets that formed with thick atmospheres or have protective chemistry might be able to counteract some of this atmospheric loss. To truly understand atmospheric retention and surface conditions, ongoing observation is crucial. The TRAPPIST-1 system offers an exciting opportunity to study multiple rocky planets in one environment. With 7 planets of varying sizes, orbits, and compositions, this system allows for a unique chance to explore planetary formation, evolution, and habitability. Some of these planets may even have resonant orbits, meaning their movements are synchronized due to gravitational interactions. These interactions could generate tidal heating, which might spark geological activity and create subsurface liquid water, similar to what we see on Jupiter's moon Europa. This heat could extend habitability, even for planets outside the traditional habitable zone. TRAPPIST-1's faint luminosity provides a stable energy source over time, which may be essential for supporting life. However, the early stages of red dwarf stars like TRAPPIST-1 are characterized by intense radiation that could have already altered the planet's atmospheres. Studying how these planets have evolved over billions of years is key to determining their potential for supporting life. Researchers continue to observe the TRAPPIST-1 system, and future missions will likely focus on detecting biosignatures or surface features that could indicate habitability. The close proximity of these planets makes it efficient to study them with the same set of instruments. If any of these planets show signs of being habitable, it could change our understanding of life in other star systems. TRAPPIST-1 isn't just a hotspot for astrobiology, it also serves as a valuable natural laboratory for studying exoplanet science. Its configuration, proximity, and orbital geometry make it one of the most promising systems for investigating the conditions necessary for life beyond Earth. On the other hand, rogue planets, also called free-floating or interstellar planets, are planetary bodies that don't orbit any star. Instead, they travel independently through space, untethered to any solar system. These planets may have originally formed around stars and been ejected through gravitational interactions, or they might have formed in isolation, much like stars do, by collapsing gas clouds. Detecting rogue planets is difficult because they emit little or no light, making traditional methods like the transit method or radial velocity ineffective. Rogue planets are instead identified using gravitational microlensing, a technique where the planet's gravity magnifies the light of a background star. Estimates suggest there could be billions of rogue planets in the Milky Way, potentially outnumbering stars. Some theories propose that early planetary systems were highly dynamic, with many planets being flung into interstellar space due to gravitational encounters with other planets or nearby stars. Such events may have been common in young stellar clusters. Despite being isolated, rogue planets could still retain internal heat from their formation, or from radioactive decay. This heat might be enough to support subsurface oceans beneath thick layers of ice, similar to conditions we find on larger icy planets. In these environments, life might exist in deep oceans, shielded from the cold vacuum of space, much like microbial life in Earth's deep-sea vents. Some rogue planets might even have moons, atmospheres, or magnetic fields. A thick hydrogen-rich atmosphere could insulate the planet, trapping heat and possibly maintaining a stable, dark climate. Theoretical models suggest that such environments might support primitive life without solar energy. However, these ideas remain speculative, and much more research is needed to confirm these possibilities. The existence of rogue planets complicates traditional definitions of habitability. These planets show that life doesn't necessarily require stellar energy. This broadens the scope of astrobiology, suggesting that geothermal and chemical energy might also support life. Studying rogue planets might help redefine the conditions required for life. However, technological limitations currently restrict our ability to study these planets in detail. Upcoming missions, like the Nancy Grace Roman Space Telescope and the ESA's Euclid mission, aim to expand microlensing surveys, which could help uncover more about these mysterious worlds. Infrared observatories may also detect thermal emissions from larger rogue planets, offering further insights into their properties. Understanding rogue planets is also important for refining our theories on planetary system evolution. The frequency and nature of planet ejections can reveal how chaotic early planetary systems were. Some researchers speculate that rogue planets could explain the origin of long-period comets or trans-Neptunian objects. These findings might even suggest that our own solar system lost planets in its early history. One intriguing idea is that rogue planets could act as vessels for panspermia, seeding life across the galaxy. If life developed on a rogue planet before its ejection, impacts or ice jets could have carried microbial material into space, possibly spreading life to other worlds. Rogue planets challenge the assumption that all planets need a star. Their existence expands the range of possible planetary environments, highlighting the diversity of planetary formation outcomes. Although difficult to detect, the sheer number of rogue planets implies that the galaxy is filled with unseen worlds drifting through interstellar space. Another cosmic mystery revolves around the possible existence of Planet 9, a hypothetical planet located far beyond Neptune. Astronomers have noticed unusual orbital patterns among distant objects in the Kuiper belt, known as trans-Neptunian objects, TNOs. These objects appear to cluster in their orbital paths, particularly in the orientation and inclination of their elliptical orbits. This anomaly led researchers to propose the existence of Planet 9, a large planet exerting gravitational influence on these distant objects. In 2016, scientists suggested that a planet with a mass between 5 and 10 times that of Earth, orbiting hundreds of astronomical units AU from the Sun, could explain these orbital alignments. If Planet 9 exists, its gravity could create the necessary perturbations to maintain the clustering of these objects over millions of years. Unlike Pluto, this hypothetical planet would not cross Neptune's orbit, staying hidden in the outer reaches of the solar system. Numerical simulations suggest that Planet 9 could have an elliptical orbit, taking between 10,000 and 20,000 years to complete one revolution. Because of its distance and location in a dense star field, detecting Planet 9 has proven difficult. No direct observation has yet confirmed its existence, but the gravitational effects on distant objects like Sedna and 2012 VP113 offer strong indirect evidence. Skeptics argue that the clustering might be due to observational bias or an incomplete survey of the outer solar system. While current searches focus on specific regions, large areas remain unexplored. As more objects are discovered and more data is gathered, the statistical significance of the clustering will be re-evaluated. Until then, Planet 9 remains a hypothesis, and astronomers continue their efforts to locate it through deep optical surveys and infrared observations. Instruments like the Subaru telescope and the upcoming Vera-C Rubin Observatory are designed to scan wide fields with high sensitivity, increasing the chances of detecting Planet 9. If it exists, it could eventually be spotted as a slow-moving point of light among the stars. The discovery of Planet 9 could shed light on the early solar system's formation. It might indicate that the solar system once had more massive planets that were ejected or migrated to distant orbits. Alternatively, Planet 9 could be a captured planet from another star system, suggesting interstellar encounters in the Sun's birth cluster. If confirmed, Planet 9 would provide valuable insight into the history and evolution of our solar system and beyond. Neptune was discovered because of its gravitational influence on Uranus, providing a prime example of how astronomical predictions can lead to groundbreaking discoveries. However, not all predictions have been accurate. Take the hypothetical planet Vulcan, for instance. This highlights the importance of empirical evidence before officially adding a new planet to our solar system. Currently, no mission is specifically designed to explore the outermost regions of our solar system. However, future spacecraft could be built to explore the trans-Neptunian region, which might help detect Planet 9 or refine our understanding of orbital dynamics at the farthest reaches of the solar system. These missions would also help improve our knowledge of small body populations and their distribution across the outer solar system. The search for Planet 9 continues to stimulate both theoretical modeling and observational efforts. If it exists, its discovery would mark a major milestone in planetary astronomy. On the other hand, if it turns out to be a myth, we'll need to reconsider alternative explanations for the orbital patterns we've observed. Either way, this search will improve our understanding of the solar system's outermost boundaries. One of the most distant areas of the solar system is the Oort cloud, a theoretical spherical shell of icy objects that stretches from about 2,000 AU astronomical units to possibly over 100,000 AU from the Sun. Proposed in 1950 by Dutch astronomer Jan Oort, the cloud was initially theorized to explain the origins of long-period comets, those with orbits lasting over 200 years. While no object in the Oort cloud has been directly observed, indirect evidence supports its existence. The comets that arrive from all directions suggest a spherical distribution, which contrasts with the flat disk-like structure of the Kuiper belt. This isotropic arrival pattern implies that the comets come from a vast, distant region evenly distributed around the Sun. The formation of the Oort cloud likely traces back to the chaotic period when the planets were still forming. During this time, icy planetesimals were scattered by the gravitational pull of the giant planets. Some were ejected into interstellar space, while others settled into stable, distant orbits, forming the Proto-Oort cloud. Over billions of years, interactions with passing stars and the gravitational influence of the Milky Way have shaped this cloud into its current spherical shape. The Oort cloud is believed to contain trillions of icy bodies, ranging in size from a few meters to tens of kilometers. These objects remain dormant for most of their lives, only becoming active comets when triggered by nearby stars, molecular clouds, or tidal forces from the galaxy. Because of their immense distance, objects in the Oort cloud move incredibly slowly, with a full orbit taking millions of years. This remoteness makes them nearly invisible to current telescopes, as their reflected sunlight is far too faint to detect. The occasional appearance of a long-period comet offers a rare opportunity to study these ancient bodies as they briefly pass through the inner solar system. Studying these Oort cloud comets can provide valuable insights into the early composition of the solar system. These objects have likely remained unchanged since their formation, preserving material from the primordial solar nebula. By analyzing their composition through spectroscopy or potential sample return missions, scientists hope to reconstruct the conditions that prevailed over 4.5 billion years ago. The Oort cloud also represents the gravitational boundary of the Sun's influence, known as the Hill sphere. Beyond this region, the Sun's gravity is no longer dominant, and objects become more susceptible to external forces, such as the gravity of passing stars. This boundary effectively defines the solar system in dynamic terms, although the majority of the Sun's mass is concentrated much closer to the center. Some models divide the Oort cloud into two regions: the inner cloud or Hills cloud, which is more tightly bound and denser, and the outer cloud, which is more diffuse and easily perturbed. Together, these form a vast three-dimensional halo of icy relics surrounding the solar system. While no direct images of the Oort cloud have been obtained, future missions and surveys might help detect faint objects within it. Space telescopes capable of observing infrared or reflected light might identify these distant bodies on their long orbits. Furthermore, improved understanding of comet dynamics could lead to better models of the Oort cloud's population and structure. The Oort cloud also raises intriguing questions about interstellar exchange. Some objects may have originated in other star systems and been captured by the Sun during its early years, while others may have been ejected into interstellar space. This creates a blur between native and foreign objects on the solar system's outskirts. The study of the Oort cloud remains theoretical, but it is essential for understanding the boundaries of our solar system, the origins of comets, and the long-term stability of distant orbits. As observational techniques improve, scientists hope to uncover more direct evidence of this vast, unseen region surrounding the Sun. One of the most fascinating comets we've studied is Comet 67 P/Churyumov-Gerasimenko. In 2014, it captured global attention when the European Space Agency's Rosetta mission successfully orbited and landed a probe on the comet. The Philae lander touched down on the comet's surface, and Rosetta collected high-resolution data for over 2 years, providing us with an unprecedented look at a type of body believed to preserve primordial material from the early solar system. The surface of Comet 67P revealed a rugged landscape, complete with cliffs, pits, and a dusty coating. Analyzing the dust and gas emitted during its activity, scientists found traces of water, carbon dioxide, ammonia, and a range of organic compounds. These included simple molecules like methane and more complex carbon-based structures, some of which are considered precursors to amino acids. The Rosetta mission's instruments, such as the COSAC and Rossini spectrometers, detected key molecules like glycine, an amino acid, and phosphorus, an essential element for DNA and cell membranes. This marked the first time these compounds were definitively identified on a comet, supporting the idea that comets may have contributed prebiotic materials to early Earth. The water found on 67P had a deuterium to hydrogen ratio that was significantly different from Earth's oceans, suggesting that these types of comets were likely not the primary source of terrestrial water. However, the discovery of organic molecules on the comet was still significant, lending weight to theories of panspermia and chemical evolution. It showed that the building blocks of life can form in cold, distant regions of the solar system. Comet 67P's periodic outgassing and surface erosion provided scientists with valuable data on how sunlight triggers the release of volatiles and renews the surface. As the comet approached the Sun, jets of gas and dust originated from specific fractures and cavities, revealing the complex interplay between sunlight, internal structure, and outgassing dynamics. The Rosetta mission ended in 2016 when the spacecraft was deliberately sent to crash into the comet's surface. This final descent offered close-up images and composition readings, further enriching the dataset. The legacy of Rosetta continues to shape cometary science and mission planning. Comets like 67P are crucial for understanding solar system history because they preserve ancient materials that have been shielded from solar radiation and geological changes. These bodies are ideal targets for studying the early conditions that may have led to the origin of life on Earth. By comparing 67P with other comets studied by spacecraft or ground-based telescopes, scientists are building a clearer picture of comet diversity. Differences in composition, activity, and morphology suggest that comets may have formed in different environments and followed various evolutionary paths within the solar nebula. Future missions might return samples from comets or deploy more advanced landers to analyze these organic compounds with greater precision and test how they might behave under early Earth-like conditions. These efforts will enhance our understanding of the role comets played in seeding life across planetary systems. In addition to comets, there are phenomena in the universe that continue to puzzle scientists, such as ultra-high-energy cosmic rays, UHCRs. These atomic nuclei, mostly protons or heavier elements, reach Earth with energies exceeding 10 circumflex, 18 electron volts, and some have been recorded at energies beyond 10 circumflex, 20 eV. These particles travel at nearly the speed of light, striking Earth's atmosphere with immense energy and creating showers of secondary particles that spread over large areas. These cosmic rays are detected indirectly by ground-based observatories like the Pierre Auger Observatory in Argentina and the Telescope Array in Utah. The extreme energies involved suggest that their origins lie in the most violent astrophysical environments, such as active galactic nuclei, gamma-ray bursts, or shock fronts in colliding galaxy clusters. Directional data for cosmic rays is limited due to the fact that these particles are charged and can be deflected by interstellar magnetic fields, making it difficult to trace their origins. One of the perplexing features of cosmic rays is the so-called Greisen-Zatopin-Kuzmin cutoff, a theoretical energy limit that suggests cosmic rays should lose energy due to interactions with photons from the cosmic microwave background before they reach Earth. However, some cosmic rays exceed this expected energy threshold, and the reasons behind these anomalies remain unclear. The composition of ultra-high-energy cosmic rays, OCRs, is still under investigation. While many appear to be protons, others may be made of heavier elements like iron. Determining the exact mass composition is crucial for identifying the sources and mechanisms responsible for accelerating these particles. Despite decades of observation, no clear astrophysical source has been definitively linked to the highest energy cosmic rays. Some patterns suggest that these cosmic rays may cluster in certain regions of the sky, but the statistical evidence is not yet strong enough to confirm any particular source. This has led to speculation about more exotic origins, such as decaying superheavy particles from the early universe or topological defects in space-time. New detection techniques aim to improve the sensitivity and range of cosmic ray observatories. Space missions like POEM, Probe of Extreme Multi-Messenger Astrophysics, are being proposed to observe UHCR air showers from orbit. This would increase the detection of these rare events and improve angular resolution, offering new insights into these mysterious particles. Studying OCRs is not only important for astrophysics, but also for particle physics. These cosmic rays carry energies far beyond what is achievable in human-made particle accelerators, providing a natural testbed for the fundamental interactions of quantum chromodynamics, QCD, and possibly even physics beyond the standard model. Anomalies in the profiles of cosmic ray showers or particle ratios may reveal unknown phenomena. Furthermore, cosmic ray data helps scientists understand magnetic fields in both our galaxy and intergalactic space. The deflection of cosmic rays provides valuable information about the structure and strength of these invisible fields, which influence the movement of particles throughout the cosmos. Understanding UACRs is crucial for improving our models of cosmic accelerators, as well as the extreme physical conditions that can generate such high energies. The mechanisms involved are closely linked to high-energy radiation, relativistic jets, and the intense activity around black holes. Despite the challenges in studying UACRs as detection methods improve and more data becomes available, researchers hope to pinpoint their origins and uncover the forces capable of accelerating matter to such extraordinary speeds. One of the most violent events in the universe is gamma-ray bursts, GRBs, which are brief but extremely energetic flashes of gamma radiation. These bursts can outshine entire galaxies for several seconds. First detected in the 1960s by military satellites monitoring nuclear tests, GRBs have since become a major topic in high-energy astrophysics. There are two main types of GRBs: short-duration bursts that last less than 2 seconds, and long-duration bursts that can last anywhere from a few seconds to several minutes. Long-duration GRBs are typically associated with the collapse of massive stars into black holes, often accompanied by supernova explosions. When the star's core collapses, it forms a black hole, emitting twin jets of high-energy particles that travel at nearly the speed of light. If one of these jets is aligned with Earth, we observe a powerful burst of gamma rays. These long-duration bursts usually occur in distant star-forming galaxies. On the other hand, short-duration GRBs are thought to result from the merger of compact objects like neutron stars, or a neutron star merging with a black hole. These catastrophic events release immense energy in the form of gamma rays and gravitational waves. The detection of both gamma ray and gravitational wave signals from a single event, known as GW 170817 in 2017, confirmed this theory, marking a breakthrough in multi-messenger astronomy. Despite their brief nature, GRBs can have significant effects. If one were to occur within a few thousand light-years of Earth and be directed toward us, it could damage our atmosphere, particularly the ozone layer. Fortunately, most GRBs originate from billions of light-years away, so this is not a current concern. The light curves of GRBs often show an initial bright flash followed by an afterglow in X-ray, optical, and radio wavelengths. These afterglows allow astronomers to pinpoint the burst's location, study its host galaxy, and measure its redshift. By tracing these bursts to the early universe, we have observed GRBs that occurred only a few 100 million years after the Big Bang. GRBs serve as powerful tools for studying distant galaxies, star formation, and the intergalactic medium at high redshifts. Satellites like NASA's SWIFT and the Fermi Gamma Ray Space Telescope play key roles in GRB detection. SWIFT, for example, can rapidly reorient itself to capture afterglows in various wavelengths, while Fermi provides detailed coverage of gamma ray energies. These missions work alongside ground-based telescopes to gather comprehensive data. The energy released in a typical GRB is staggering. A single burst can emit more energy in just a few seconds than the Sun will produce over its entire 10 billion year lifespan. The mechanism behind this involves extreme conditions such as strong magnetic fields near black holes, relativistic jets, and the acceleration of particles at nearly light speed. GRBs may also be linked to the formation of heavy elements. Short-duration GRBs, in particular, occur in neutron-rich environments, which are ideal for the rapid neutron capture process, the R process responsible for creating elements like gold and platinum. Studying the remnants of these bursts allows us to trace the cosmic origins of these elements. Theoretical models of GRBs continue to evolve, with questions still remaining about jet structure, the role of magnetic fields, and the conditions required to launch a GRB. Advanced simulations are refining these models and predicting observational signatures that can be tested with future instruments. Upcoming missions like Theseus and Ultrazet aim to observe GRBs from even earlier epochs of the universe. These observations could provide clues about the first generations of stars and the period of reionization. By pushing the limits of observation, GRBs will remain crucial for exploring the cosmic frontier. One fascinating future event in the universe is the collision of the Andromeda Galaxy M31 with our own Milky Way. Located about 2.5 million light-years away, Andromeda is the nearest spiral galaxy to the Milky Way and the largest member of our local group. Despite its vast distance, precise measurements show that Andromeda is moving toward us at about 110 kilometers per second due to mutual gravitational attraction. This motion was first detected through Doppler shift analysis, which showed a consistent blue shift, indicating that Andromeda is approaching rather than receding. In about 4 billion years, the Andromeda and Milky Way galaxies will collide in a massive galactic merger. Although stars in both galaxies are unlikely to collide due to the vast distances between them, their gravitational interactions will reshape their structures. Computer simulations suggest that tidal forces during the merger will stretch and warp the galaxies, creating long tails of stars and gas. Eventually, the two galaxies will merge into a single elliptical or lenticular galaxy, often referred to as Milkoma. During the early stages of the merger, star formation may be triggered as gas clouds are compressed under gravitational stress. This could lead to a temporary burst of stellar birth, known as a starburst. Later, as gas is depleted and heated, star formation will slow, leading to a more quiescent state typical of elliptical galaxies. The supermassive black holes at the centers of both galaxies will likely interact as well. Over time, they may spiral toward each other and eventually merge, releasing gravitational waves detectable by future observatories. This merger of central black holes would provide valuable insights into black hole dynamics and galactic evolution. While Earth will still be here when the merger begins, the Sun will be nearing the end of its life cycle, transitioning into a red giant. The merger will dramatically alter the night sky, as Andromeda grows larger before finally merging with the Milky Way. Despite its dramatic nature, the merger will not pose a threat to life on Earth, as the slow pace of the event and the low density of stars make catastrophic collisions highly improbable. The main effects will be visual and structural on a galactic scale, but not destructive on a planetary level. Studying this future merger will help astronomers understand the life cycle of galaxies and provide valuable comparisons with other galactic mergers occurring at different stages. The study of galaxy mergers reveals that these events are not just rare but common, playing a central role in shaping the universe. The upcoming collision between the Milky Way and Andromeda is just one example of this larger cosmic process, which also involves nearby galaxies like the Triangulum Galaxy, MUN33. These mergers will contribute to the formation of a more complex cosmic interaction as the local group of galaxies slowly consolidates into a larger structure over cosmic timescales. By analyzing the motions, mass distributions, and morphologies of galaxies, astronomers are developing increasingly accurate models of how galaxies evolve over billions of years. The impending merger between the Milky Way and Andromeda is not just a prediction, it's a crucial piece in understanding the formation, growth, and transformation of galaxies over time. This cosmic event offers an opportunity to learn about the forces that shape galaxies, and studying such mergers gives us insight into the future evolution of our own galaxy. The age of the universe, currently estimated to be 13.8 billion years, is determined through multiple lines of evidence. The most direct method involves studying the expansion of the universe, which was first observed by Edwin Hubble in the 1920s. By measuring the redshift of galaxies and their distances, astronomers discovered that the universe is expanding uniformly in all directions. This suggests that the universe originated from a much denser and hotter state. Tracing this expansion backward, using the Hubble constant, allows scientists to estimate the universe's age, although the precise measurement of this constant is still a work in progress. Various methods, such as observing Cepheid variables, supernovae, and gravitational lensing, contribute to these estimates, all of which converge on the same general timeline. A key piece of evidence supporting this age estimate comes from the cosmic microwave background, CMB, the faint radiation left over from the early universe. Space telescopes like COBE, WMAP, and Planck have mapped the CMB with incredible precision, revealing temperature fluctuations that provide insights into the density, composition, and geometry of the early universe. Using the Lambda Cold Dark Matter LCDM model, which takes into account dark energy, dark matter, and radiation, scientists have been able to simulate the universe's evolution and match it to the observed data, reinforcing the 13.8 billion year timeline. Another approach to determining the universe's age involves studying the oldest known stars and star clusters. Globular clusters, which contain some of the oldest stars, have ages estimated through stellar evolution models and nucleosynthesis. These estimates typically fall around 12 to 13 billion years, providing a lower limit for the universe's age and aligning with cosmological data. White dwarfs, the remnants of low-mass stars, also help confirm this estimate. By observing the cooling rates of white dwarfs and studying their luminosity and temperature, astronomers can estimate how long they've been cooling, further supporting a universe older than 13 billion years. Additionally, theoretical models of structure formation offer insight into the universe's age. Simulations of how matter clumped together to form galaxies and clusters over billions of years match the observed large-scale structure of the universe, reinforcing the 13.8 billion year estimate. Though small uncertainties remain, especially regarding measurements of the Hubble constant, these do not significantly alter the overall age estimate. With future advancements in technology, measurements will become more precise, and upcoming space telescopes may provide alternate methods for cross-checking the cosmic timeline. Understanding the age of the universe is more than just a matter of numbers. It is fundamental to all of modern cosmology. It sets the timeline for the formation of galaxies, stars, planets, and life itself. Knowing the universe's age provides context for every observation made across the night sky and informs theories about its ultimate fate. Stars are born in dense, cold regions of space known as giant molecular clouds, GMCs, which are primarily made up of molecular hydrogen, helium, dust, and trace elements. These clouds can span dozens to hundreds of light years and contain enough material to form thousands of stars. The low temperatures of these clouds, typically between 10 and 20 Kelvin, allow gravity to overcome the internal pressure and initiate the collapse of gas. Within these massive clouds, regions of higher density form due to turbulence or external triggers, such as shock waves from nearby supernovae. These dense clumps, known as prestellar cores, contract under gravity, causing the temperature to rise at their center. If the core's mass is sufficient, the temperature will eventually reach millions of degrees, triggering nuclear fusion and creating a new star. This collapse is not smooth, however. Angular momentum causes the infalling material to form a rotating disk around the protostar. This disk feeds the growing star and may eventually evolve into a planetary system. Jets and outflows from the poles of the protostar help regulate its mass and clear away surrounding material, allowing radiation to escape. Magnetic fields also play a significant role in star formation. They can slow down the collapse, channel material along field lines, and even influence the direction of the jets. The presence of dust grains in the cloud helps absorb visible light, which is then re-emitted in the infrared, making these regions observable with infrared telescopes like Spitzer and ALMA. GMCs are not uniform in structure. They contain filaments, knots, and cavities that are shaped by gravity, turbulence, radiation, and feedback from nearby stars. Some regions fragment, leading to the formation of multiple stars, often resulting in binary or multiple star systems. Massive stars form quickly and can disrupt their environment through intense radiation and stellar winds, affecting nearby star formation. However, star formation efficiency within a GMC is generally low, with only a small fraction of the cloud's mass eventually turning into stars before the remaining gas is dispersed. Feedback from newly formed stars such as ionizing radiation and supernovae plays a crucial role in dispersing the remaining gas, halting further star formation in that region. The time it takes for a star to form varies depending on its mass. Low-mass stars like the Sun may take tens of millions of years to reach the main sequence, while high-mass stars can form in less than 1,000,000 years and live only a few more years before exploding as supernovae. Studying different regions of star formation at various stages allows astronomers to piece together a more complete picture of stellar evolution. Star-forming regions like the Orion Nebula and the Eagle Nebula, with their proximity and visibility, provide excellent laboratories for studying these processes. Star formation also leads to chemical enrichment, as molecules like water, carbon monoxide, and complex organics form on dust grains. These compounds may later be incorporated into comets or planets, potentially contributing to prebiotic chemistry. The study of star formation in GMCs is essential for understanding astrophysics, as it lays the foundation for galaxy evolution, planet formation, and the development of complex chemistry. By investigating how stars are born, scientists gain insight into the origins of the elements and the conditions that lead to the creation of planetary systems like our own. Pulsars are neutron stars, dense remnants left behind after a massive star ends its life in a supernova. When the collapsing core retains enough mass but not enough to form a black hole, it compresses into a neutron star, which is about 20 kilometers in diameter, but contains more mass than the Sun. These stars rotate rapidly and emit beams of electromagnetic radiation from their magnetic poles. If the star's rotation axis and magnetic axis are misaligned, the radiation beams sweep across the sky like a lighthouse, and when one of these beams points toward Earth, we detect a pulse of energy at regular intervals. Pulsars are some of the most precise natural clocks in the universe. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, initially mistaken for a signal from extraterrestrial intelligence due to its regularity. Since then, thousands of pulsars have been identified across the galaxy using radio and X-ray telescopes. The stability of their pulses allows for incredibly accurate timing studies, making them vital for understanding the universe. Millisecond pulsars in particular are of great interest due to their extraordinary precision. These pulsars rotate even faster, making them even more reliable as cosmic timekeepers. Millisecond pulsars are a special type of neutron star that have been sped up through the process of accreting matter from a companion star. This accretion transfers angular momentum to the pulsar, causing it to spin at extraordinary rates, often over 700 times per second. Their pulse timing is so precise that scientists can use them as cosmic clocks to test theories of gravity and detect low-frequency gravitational waves. A key application of pulsars is in pulsar timing arrays, where networks of millisecond pulsars are monitored for tiny deviations in their pulse arrival times. These minute variations could reveal the presence of gravitational waves, which are caused by massive cosmic events like merging supermassive black holes. Pulsars also provide an invaluable window into the physics of matter under extreme densities. The interiors of these stars contain states of matter that can't be reproduced in labs, such as superfluid neutrons or even exotic quark matter. By studying their rotation, glitches, and magnetic fields, astrophysicists can infer the properties of nuclear matter under immense pressure. Some pulsars emit across multiple wavelengths, including gamma rays and visible light. With instruments like Fermi and NICER, scientists can conduct multi-wavelength studies, diving deeper into their magnetospheres, emission mechanisms, and thermal evolution. Each wavelength reveals different layers of the pulsar's structure and energy output, expanding our understanding of these mysterious objects. The rotation of pulsars gradually slows over time due to the loss of energy through radiation. By measuring the spin-down rate, scientists can estimate the age of a pulsar and learn more about its magnetic field strength. Occasionally, pulsars exhibit glitches, sudden increases in rotation speed, which are believed to result from internal restructuring. These glitches offer unique insights into the inner dynamics of pulsars. Binary pulsars, especially systems where both stars are neutron stars, are valuable for testing general relativity. For example, the Hulse-Taylor binary system showed orbital decay that matched predictions for energy loss via gravitational waves, leading to the 1993 Nobel Prize in Physics. More of these systems are helping refine our understanding of gravity. Pulsars located in globular clusters or near the galactic center are also instrumental in mapping the gravitational potential of the Milky Way. Their distribution and motion give us critical clues about the galaxy's structure, dark matter content, and dynamical history. These pulsars help identify areas rich in stellar remnants and high-energy activity, making them key tools for studying the Milky Way. As research continues, pulsars remain indispensable for advancing multiple fields in astrophysics. Their precision, versatility, and resilience make them reliable beacons not only for exploring the cosmos, but also for testing the fundamental laws of physics. From timing planetary masses to probing gravitational waves, pulsars are far more than dead stars. They're instruments of cosmic measurement. The Sun, currently in a stable phase of its life cycle as a G-type main sequence star, derives its energy from nuclear fusion in its core. Hydrogen atoms fuse into helium, releasing energy that counterbalances the inward pull of gravity and sustains the Sun's size and luminosity. This balance has lasted for approximately 5 billion years, and the Sun is currently halfway through this stable phase. However, over time, as the hydrogen in the core becomes depleted, the Sun will no longer be able to maintain equilibrium through fusion alone. As a result, the core will contract, heat up, and cause the outer layers to expand and cool. This signals the start of the red giant phase, during which the Sun will grow to several hundred times its current size, potentially engulfing the inner planets, including Earth. During the red giant phase, helium fusion will begin in the core through the triple alpha process, forming carbon and oxygen. Fusion will occur in shells around the core, while the outer layers remain unstable and convective. The Sun will experience thermal pulses, resulting in episodes of mass loss and increasing instability. Once the helium is exhausted, the Sun will not have enough mass to ignite subsequent fusion stages like carbon burning. Instead, it will shed its outer layers, creating a planetary nebula, a glowing shell of ionized gas illuminated by the hot core. This nebula can persist for tens of thousands of years before dissipating into the interstellar medium. The remaining core, now a white dwarf, will be an extremely dense, Earth-sized object composed mainly of carbon and oxygen. With no fusion to sustain it, the white dwarf will gradually cool and fade over billions of years, radiating away its remaining heat. This remnant will endure long after the planetary nebula has vanished. Planetary nebulae are significant sources of chemical enrichment in the galaxy, as the gas expelled by stars like the Sun contains elements such as carbon, nitrogen, and oxygen, which will later be incorporated into new generations of stars and planets. This enrichment plays a fundamental role in the evolution of galaxies. By studying stars in various stages of their life cycles, astronomers can better predict the Sun's future. Observing red giants, planetary nebulae, and white dwarfs in nearby star clusters allows scientists to build models that describe solar evolution in great detail. These models are calibrated with solar data and tested against observed stellar populations. The Sun's transition into a red giant will occur gradually over hundreds of millions of years, giving any surviving Earth life plenty of time to adapt or relocate. Long before this transformation, the increasing luminosity of the Sun will likely render Earth uninhabitable, boiling away its oceans. The Sun's white dwarf phase could last for trillions of years, far exceeding the current age of the universe. Eventually, it may cool into a black dwarf, although this process is purely theoretical at this stage, as the universe is not yet old enough for black dwarfs to exist. Understanding the Sun's fate provides valuable insight into the future of similar stars throughout the galaxy. It also informs studies of habitable zones, planetary system evolution, and the long-term prospects for life. As a medium-mass star, the Sun represents the most common type of star in the universe. Using space-based observatories like Gaia and Hubble, astronomers continue to monitor stars in every phase of their life cycle. These observations help refine models of stellar structure, fusion processes, and mass loss, contributing to a more complete picture of the Sun's future and its lasting impact on the solar system. Dark matter halos, the invisible structures that surround galaxies and galaxy clusters, are some of the most fascinating and mysterious components of the universe. Although dark matter doesn't emit, absorb, or reflect light, its presence is undeniable due to its gravitational effects. The concept of dark matter emerged when astronomers noticed that galaxies were rotating at speeds that couldn't be explained by visible matter alone. Without an unseen mass component, the stars on the outer edges of galaxies would be flung away by centrifugal force. However, observations of galaxy rotation curves revealed that star velocities remain constant or even increase far beyond the visible edge of galaxies, indicating the presence of an extended, unseen mass distribution. These dark matter halos can contain up to 10 times more mass than the visible galaxy itself. Gravitational lensing further supports the existence of dark matter halos. When light from distant sources passes through a massive object like a galaxy cluster, the object bends the light, distorting the image of the background source. By measuring the amount of light distortion, scientists can map the total mass of the system, and the results show that most of the mass resides in a halo-like structure far beyond the visible galaxy. Simulations of large-scale cosmic structure heavily rely on dark matter halos. These simulations help reproduce the filamentary web of galaxies that we see today, showing how galaxies are distributed, shaped, and clustered by the gravitational influence of dark matter. Dark matter halos come in varying sizes, from small subhalos surrounding dwarf galaxies to massive halos that bind entire galaxy clusters. Their formation began early in the universe's history, as slight density fluctuations grew under the influence of gravity. These clumps of dark matter merged and accreted over billions of years, providing the gravitational wells into which ordinary matter could fall and form galaxies. Galaxies evolve within these halos, and the properties of the halo, such as its mass and environment, affect the galaxy's star formation rate, morphology, and satellite population. Although simulations predict a dense central core within dark matter halos, observations sometimes show a flatter distribution, and resolving this discrepancy remains an active area of research. Satellite galaxies orbiting larger hosts provide further clues about halo structure as they trace the gravitational field and reveal substructures within the halo. Some halos, like the ones surrounding the Milky Way, are believed to contain hundreds of such subhalos, though only a fraction of them host visible stars. While efforts to directly detect dark matter particles like WIMPs or axions have yet to succeed, the gravitational evidence for dark matter halos leaves little doubt about their existence. Future detectors and collider experiments may help confirm the particle nature of dark matter. Dark matter halos are invisible structures that surround galaxies and galaxy clusters. Though they don't emit light, we know they exist due to their gravitational effects. When galaxies collide, the visible stars and gas may be disrupted, but the dark matter halos pass through each other without much disturbance. The famous Bullet cluster illustrates this, showing dark matter and hot gas separated, mapped using X-ray and lensing data. Understanding these halos is essential for understanding how galaxies grow and evolve, as they provide the framework on which galaxies are built. Even though we can't see them, their gravitational pull shapes the universe's structure. Dark energy is a mysterious force that drives the accelerated expansion of the universe. Discovered through observations of distant supernovae in the late 1990s, it suggests that the universe is not only expanding, but its expansion is speeding up. This discovery led to the idea of a cosmological constant, a form of energy that doesn't change as space expands, pushing galaxies apart. Dark energy makes up about 68% of the universe's total energy content. Unlike matter, which clumps under gravity, dark energy is evenly spread throughout space. Its effects are most noticeable on large scales, dominating the expansion of the universe. Scientists study dark energy using methods like measuring cosmic microwave background radiation and observing large-scale structures in the universe. Surveys and missions like WMAP and the Vera Rubin Observatory are helping to map out dark energy's influence on the universe's expansion. Though we don't fully understand it, dark energy plays a huge role in shaping the future of the cosmos. If it continues to push space apart, galaxies may drift too far from each other to interact, leading to an increasingly empty universe. Some models even predict a big rip, where the expansion eventually tears apart all structures. Galaxy mergers are common events that shape the evolution of the universe. These collisions occur when two or more galaxies are drawn together by gravity. The Milky Way itself will merge with the Andromeda Galaxy in about 4.5 billion years. As the galaxies approach, tidal forces stretch them out, creating long trails of stars and gas known as tidal tails. Eventually, the galaxies lose orbital energy, causing their cores to merge into one larger galaxy. During this process, gas clouds are compressed, triggering intense bursts of star formation known as starbursts. The result of a merger depends on the size of the galaxies involved. Minor mergers involve a larger galaxy absorbing a smaller one, often leaving the larger galaxy's structure intact. Major mergers, where galaxies of similar sizes collide, can drastically change their shape and dynamics. Spiral galaxies that merge often turn into elliptical galaxies, which have less gas for new stars. These mergers also contribute to the growth of massive galaxies and their dark matter halos, forming larger structures like galaxy groups and clusters. Observing galaxy mergers helps scientists understand the formation of galaxies and their evolution over time. Instruments like the Hubble Space Telescope and ALMA have captured detailed images of these collisions. By studying these interactions, we can learn about the distribution of dark matter, star formation rates, and the behavior of central black holes. Merging galaxies also offer insights into how galaxies and their structures evolve over billions of years. Einstein rings are a fascinating example of how gravity bends light. This phenomenon occurs when the gravitational field of a massive object, like a galaxy, distorts and magnifies the light from a more distant source. This effect, predicted by Einstein's theory of general relativity, happens when a background galaxy or quasar aligns perfectly with a foreground galaxy and the observer. The result is a ring of light, known as an Einstein ring, that we can observe from Earth. Einstein rings are a result of gravitational lensing, where the gravity of a massive object bends the light from a more distant object behind it. This bending distorts the light, creating a symmetrical arc or full ring known as an Einstein ring. The size of this ring depends on the mass of the foreground object and the distance between the observer, lens, and source. More massive objects create larger rings. By observing these rings, astronomers can estimate the mass of the lensing object, including its dark matter content. Einstein rings also act as natural telescopes, allowing us to study distant galaxies that would otherwise be too faint to see. They magnify and distort background light, giving us detailed views of early galaxies. While full rings are rare, partial rings or arcs are more common and still useful for mapping mass and studying galaxy evolution. Instruments like the Hubble Space Telescope and ALMA have captured many Einstein rings, each offering a unique opportunity to learn about dark matter and galaxy formation. Gravitational lensing can also help track how galaxies accumulate mass and form stars across cosmic time. Space telescopes like the James Webb Space Telescope and Hubble allow us to observe the universe across different parts of the electromagnetic spectrum, not just visible light. Each part of the spectrum reveals different physical processes that help us understand celestial objects and cosmic events more fully. For example, visible light telescopes provide high-resolution images of stars and galaxies, but they miss high-energy processes happening in space. Infrared telescopes, like the James Webb and Spitzer, can penetrate dust clouds, revealing star-forming regions, cooler objects, and early galaxies whose light has been stretched due to the expansion of the universe. Ultraviolet telescopes observe high-energy emissions from hot stars and active galactic nuclei, and are crucial for mapping star formation and chemical composition. Since Earth's atmosphere blocks most ultraviolet light, space-based telescopes are necessary for these studies. X-ray telescopes like Chandra and XMM Newton observe high-energy processes like black hole activity, hot gas in galaxy clusters, and neutron stars. These observations reveal extreme conditions of temperature and density. Gamma-ray telescopes such as Fermi explore the universe's most energetic events, including gamma-ray bursts and particle collisions, and provide insights into dark matter annihilation. Because gamma rays require specialized detection methods, these telescopes are designed to study high-energy cosmic phenomena. Radio telescopes, which can operate both on Earth and in space, are key for studying cold gas clouds, cosmic microwave background fluctuations, and synchrotron emissions. Space-based radio telescopes extend baseline distances for interferometry, improving resolution. The Planck satellite mapped the cosmic microwave background, CMB, in exquisite detail, providing valuable information about the early universe. Space telescopes often coordinate multiband observations, studying a single object across radio, infrared, optical, UV, X-ray, and gamma-ray bands. This approach allows scientists to see cosmic phenomena at different energy scales, from cool gas to violent black hole jets. Each type of telescope has its own specialized equipment, such as cooling systems for infrared instruments and grazing incidence mirrors for X-ray and gamma-ray telescopes. With advancements in detector technology, optics, and thermal control, upcoming missions like the Roman Space Telescope and Athena will increase the sensitivity and resolution of our observations. These innovations will help astronomers uncover new discoveries across the universe. By observing the universe in all parts of the electromagnetic spectrum, space telescopes provide a comprehensive view of the cosmos, revealing hidden structures, processes, and objects that help us understand the universe better.